Hello guys, recording in progress. Today is Tuesday, July 12th, 2022. Today we will start with the clustering. We'll watch some videos about the clustering from two professors. Then we will move to dimensionality reduction and the principal component analysis, which is feature extraction, not a feature selection. And you will differentiate between what do we mean by feature selection and feature extraction. Then we will move toward anomaly detection, and at the same time we will explain some optimization technique in the second session, and how to reduce the computational complexity of our machine learning model. On that machine learning model, that's one of my published paper 2 years ago, we use different techniques and different optimization techniques. So this would be recover like the whole concept that we studied till today, except the unsupervised learning techniques. So I'll share my screen right now and we will start.
I'd like to start to talk about clustering.
Is the sound clear, guys? Okay, sounds good. Sounds good. Thank you, guys.
This will be exciting because this is our first unsupervised learning algorithm where we learn from unlabeled data instead of from labeled data. So what is unsupervised learning? I briefly talked about unsupervised learning at the beginning of the class, but it's useful to contrast it with supervised learning. So here's a typical supervised learning problem where we're given a labeled training set, and the goal is to find a decision boundary that separates the positive labeled examples and the negative labeled examples. So the supervised learning problem in this case is given a set of labels to fit a hypothesis to it. In contrast, in the unsupervised learning problem, we're given data that does not have any labels associated with it. So we're given data that looks like this. Here's a set of points, and there are no labels. And so our training set is written just x1, x2, and so on up to xm, and we don't get any labels y. And that's why the points plotted up on the figure don't have any labels with them. So in unsupervised learning, what we do is we give this sort of unlabeled training set to an algorithm, and we just ask the algorithm, find some structure in the data for us. Given this data set, one type of structure we might have an algorithm find is that it looks like this data set has points grouped into two separate clusters. And so an algorithm that finds clusters like the ones I've just circled is called a clustering algorithm. And this will be our first type of unsupervised learning, although there will be other types of unsupervised learning algorithms that we'll talk about later that finds other types of structure or other types of patterns in the data other than clusters. We'll talk about this after we've talked about clustering. So what is clustering good for? Early in this class, I'd already mentioned a few applications. One is market segmentation, where you may have a database of customers and want to group them into different market segments so you can sell to them separately or serve your different market segments better. Social network analysis. There are actually groups that have done this. Things like looking at a group of people's social networks, so things like Facebook, Google+, or maybe information about who are the people that you email the most frequently and who are the people that they email the most frequently, and to find coherent groups of people. So this would be another maybe clustering algorithm where you want to find who are the coherent groups of friends in a social network. Here's something that one of my friends actually worked on, which is use clustering to organize compute clusters or to organize data centers better, because if you know which computers in the data center and the cluster tend to work together, you can use that to reorganize your resources and how you lay out the networks and how you design your data center and communications. And lastly, something that actually another friend worked on, using clustering algorithms to understand galaxy formation and using that to understand how to understand astronomical data. So that's clustering, which is our first example of an unsupervised learning algorithm. In the next video, we'll start to talk about a specific clustering algorithm.
This course is about systems and system thinking. We use
In the clustering problem, we are given an unlabeled dataset, and we would like to have an algorithm automatically group the data into coherent subsets or into coherent clusters for us. The k-means algorithm is by far the most popular and by far the most widely used clustering algorithm. And in this video, I'd like to tell you what the k-means algorithm is and how it works. The k-means clustering algorithm is best illustrated in pictures. Let's say I want to take an unlabeled dataset like the one shown here, and I want to group the data into two clusters. If I run the k-means clustering algorithm, here's what I'm going to do. The first step is to randomly initialize 2 points called the cluster centroids. So these two clusters here, these are called the cluster centroids.
Guys, concentrate about this point. The k-means algorithm, when it try to do like two clusters, as the example in front of us, it will try to decide where is the cluster centroid. What is the cluster centroid? Because it will start measuring certain thing to make sure or to decide that this data point, it referred to cluster, the blue cluster, or to the red cluster, based on certain criteria. So please try to understand what do you mean by cluster centroid. Concentrate about this point.
And I have two of them because I want to group my data into two clusters. K-means is an iterative algorithm, and it does two things. First is a cluster assignment step, and second is a move centroid step. So let me tell you what those things mean. The first of the two steps in the inner loop of k-means is this cluster assignment step. What that means is that it's going to go through each of the examples, each of these green dots shown here, and depending on whether it's closer to the red cluster centroid or the blue cluster centroid, it is going to assign each of the data points to one of the two cluster centroids. Specifically, what I mean by that is going to go through your data set and color each of the points either red or blue, depending on whether it's closer to the red cluster centroid or the blue cluster centroid. And I've done that in this diagram here. So that was the cluster assignment step. The other part of k-means, the inner loop of k-means, is the move centroid step. And what we're going to do is we're going to take the two cluster centroids, that is the red cross and the blue cross, and we're going to move them to the average of the points colored the same color. So what I'm going to do is look at all the red points and compute the average, that's really the mean of the location of all the red points, and we're going to move the red cluster centroid there. And the same thing for the blue cluster centroid. Look at all the blue dots and compute their mean, and then move the blue cluster centroid there. So let me do that now. We'll move the cluster centroids as follows, and I've now moved them to their new means, right? So the red one moved like that, and the blue one moved like that, and the red one moved like that. And then we go back to another cluster assignment step. So we're again going to look at all of my unlabeled examples, and depending on whether it's closer to the red or the blue cluster centroid, I'm going to color them either red or blue. So I'm going to assign each point to one of the two cluster centroids. So let me do that now. And so the colors of some of the points just changed. And then I'm going to do another move centroid step. So I'm going to compute the average of all the blue points, compute the average of all the red points, and move my cluster centroids like this. And so let's...
Guys, k-means algorithm contains multiple iteration. In each iteration, it will assign a cluster centroid. Then what do we mean by mean? It will take the mean position of all. Then it will assign the point to the cluster. At that time, we will have a new mean and a new cluster centroid. Then with the second iteration, we'll do the same. We will calculate the new mean. We put the centroid, then we will assign the point to the cluster. And it will keep going till we find the best centroid and the best cluster, as you see here.
Let's do that again. Let me do one more cluster assignment step. So color each point red or blue based on what it's closer to, and then do another move centroid step. And we're done. And in fact, if you keep running additional iterations of k-means from here, the k-means, the cluster centroids will not change any further, and the colors of the points will not change any further. And so, this is the...
So here you will ask a question, how many iterations do I do? As Andrew and G mentioned, that we will keep changing the centroid based on the new the mean of the new data points till there are no more changes in the centroid position, which means we reach to the best clustering using k-mean algorithm. Questions still here? Questions? Okay, let's continue.
At this point, k-means has converged, and it's done a pretty good job finding the two clusters in this data. Let's write out the k-means algorithm more formally. The k-means algorithm takes two inputs. One is a parameter k, which is the number of clusters you want to find in the data. I'll later say how we might go about trying to choose k, but for now, let's just say that we've decided we want a certain number of clusters, and we're going to tell the algorithm how many clusters we think there are on the data set. And then k-means also takes as input this sort of unlabeled training set of just the x's, and because this is unsupervised learning, we don't have the labels y anymore.
So k-mean algorithm take two input. The first input is the number of a cluster. How many cluster do I want? For example, assume that we want to cluster the student based on their performance. I can make pass and fail, two clusters. Maybe another researcher would see no, poor academic performance, fair academic performance, and good academic performance. So here I have three clusters. I can cluster the student into three clusters. One other researcher said, hey, no, I will follow Bloom's taxonomy. In a Bloom's taxonomy, I believe we have 5 or 6 student clusters, like need help, which means poor academic performance, fair academic performance, good academic performance, very good academic performance, and excellent academic performance. And as Andrew and G mentioned, this is unsupervised learning. So here we will take the X's, which mean the features, as a training set, and we don't have Y, which is the label. If we have a Y, then I can use any supervised machine learning technique like SVM, naive Bayes, KNN, these random forest or decision tree in general, these kind of techniques are supervised because I know the label. But the clustering, we don't know the label. We try to group or to find a pattern that will group a student with similar properties, which is the features, in a certain cluster. This is what do we mean by unsupervised learning. So here we have the number of cluster. I need to classify like anomaly and normal, attack and normal traffic. So 2 cluster assume. Then I send the features, and based on the features, it will try to cluster the student. I need 3 clusters. Like, as I said, poor academic performance, fair academic performance, and good academic performance. Then I input 3 clusters. And based on that, I try to cluster, and at that time I have 3 centroids, and I will work via iteration till the algorithm converge and no more changes in the centroid position. Clear, guys, about the algorithm?
And for unsupervised learning, or for k-means, I'm going to use the convention that xi is an Rn dimensional vector. And that's why my training examples are now n-dimensional rather than n+1 dimensional vectors. This is what the k-means algorithm does. The first step is that it randomly initializes k cluster centroids, which we'll call mu1, mu2, up to mu k. And so in the early diagram, the cluster centroids corresponded to the location of the red cross and the location of the blue cross. So there we had two cluster centroids. So maybe the red cross was mu1 and the blue cross was mu2. And more generally, we would have k cluster centroids rather than just two. Then the inner loop of k-means does the following. We're going to repeatedly do the following. First, for each of my training examples, I'm going to set this variable ci to be the index 1 through k of the cluster centroid closest to xi. So this was my cluster assignment step, where we took each of my examples and colored it either red or blue, depending on which cluster centroid it was closest to. Okay, so ci is going to be a number from 1 to k that tells us, is it closer to the red cross or is it closer to the blue cross? And another way of writing this is I'm going to, to compute ci, I'm going to take my ith example xi, and I'm going to measure its distance to each of my cluster centroids. This is mu and then a lowercase k, right? So capital K is the total number of centroids, and I'm going to use lowercase k here to index.
So here we are calculating the distance between the data point and the mu, which is the centroid that we choose. Currently, the chosen centroid currently in this iteration in 4.
Into the different centroids. But so ci is I'm going to sort of minimize over my values of k and find the value of k that minimizes this distance between xi and the cluster centroid, and then the value that minimizes the value of k that minimizes this, that's what gets set in ci. So here's another way of writing out what ci is. If I write the norm between xi minus mu k, then this is the distance between my ith training example xi and the cluster centroid mu subscript k. This here, that's a lowercase k. So uppercase k is going to be used to denote the total number of cluster centroids, and this lowercase k, the lowercase k is a number between 1 and capital K. I'm just using lowercase k to index into my different cluster centroids. Right, so that's lowercase k. So that's the distance between the example and the cluster centroid, and so what I'm going to do is find the value of k, of lowercase k, that minimizes this, and so the value of k that minimizes this, that's what I'm going to set as ci. And by convention, here I've written the distance between xi and the cluster centroid. By convention, people actually tend to write this as the squared distance. So we think of ci as picking the cluster centroid with the smallest squared distance to my training example xi. But of course, minimizing squared distance and minimizing the distance, that should give you the same value of ci. But we usually put in the square there just as a convention that people use for k-means. So that was the cluster assignment step.
Technology, computers, and code.
The other inner loop of k-means does the move centroid step. And what that does is, for each of my cluster centroids, so for lowercase k equals 1 through k, it sets mu k equals to the average of the points assigned to cluster. So as a concrete example, let's say that one of my cluster centroids, let's say cluster centroid 2, has training examples, 1.
So guys, here in the first step, we do cluster assignment by calculating the distance between the training sample and the current centroid, which is mu k. And as Andrew mentioned, that this is k small letter. What k capital means? K capital means the total number of k's that we use. So the second step, we need to move the centroid to be the mean of the current selected cluster based on this. Once we choose the mean, then we'll have a new mu. Then we will repeat the same process till the algorithm converge and no any changes in mu's.
5, 6, and 10 assigned to it. And what this means is really, this means that C1 equals to C5 equals to C6 equals to, and similarly, well, C10 equals to, right? If we got that from the cluster assignment step, then that means that examples 1, 5, 6, and 10 were assigned to cluster centroid 2. Then in this move centroid step, what I'm going to do is just compute the average of these four things. So I'm going to x1 plus x5 plus x6 plus x10, and then I'm going to average them. So here I have 4 points assigned to this cluster centroid, so I'm just take 1/4 of that. And now mu2 is going to be an n-dimensional vector, because each of these examples, x1, x5, x6, x10, each of them were an n-dimensional vector. And when I add up these things and divide by 4, because I have 4 points assigned to the cluster centroid, I end up with my move centroid step for my cluster centroid mu2, and this has the effect of moving mu2 to be the average of those 4 points listed here. One thing that I've sometimes been asked is, well, here we said let's let mu k be the average of the points assigned to that cluster, but what if there's a cluster? What if there's a cluster centroid with no points, with 0 points assigned to it? In that case, the more common thing to do is to just eliminate that cluster centroid, and if you do that, you end up with k-1 clusters instead of.
Okay, guys, here he's talking about an important point. What if I chose at the beginning of the running the k-means algorithm, I chose, like, for example, 5 clusters, and based on the centroid, I end up that there are 4 centroid has a value, which means that the data as maximum could be clustered into 4 clusters, and the 5th one, there are no data point around that cluster. What shall I do? I have to eliminate that cluster, and at that time, the output of the k-means algorithm would be k-1 cluster. I chose at the beginning 5 cluster, and I end up that I only have 4 clusters. Is that clear?
Of k clusters. But sometimes if you really need k clusters, then the other thing you can do if you have a cluster centroid with no points assigned to it is you can just randomly reinitialize that cluster centroid. But it's more common to just eliminate a cluster if somewhere during k-means it ends up with no points assigned to that cluster centroid.
Another solution some programmer or some machine learning developers do, what they normally do, they reinitialize the 5th cluster and see the value of the 5th cluster, maybe the centroid position, the randomly selected centroid position at the beginning. Let us end up with that this cluster has no data point. Then they try to reinitialize it to find maybe another chance to have 5 clusters. But if not, then eliminate it. As Andrew and G mentioned, that it's better to eliminate it from the beginning. However, you can reinitialize the 5th one value and see how it's going. But believe me, most of them will end to eliminate that cluster, that the data is like the data points are coming into 4 cluster, the 5th cluster is not available, or it will lead up to like wrong clustering to find the 5th one. Sometimes it's work, but in rare cases.
That can happen, although in practice it happens not that often. So that's the k-means algorithm. Before wrapping up this video, I just want to tell you about one other common application of k-means, and that's to the problems with non-well separated clusters. Here's what I mean. So far we've been picturing k-means and applying it to data sets like that shown here, where we have 3 pretty well separated clusters, and we'd like an algorithm to find maybe the 3 clusters for us. But it turns out that very often k-means is also applied to data sets that look like this, where there may not be several very well separated clusters. Here's an example application to t-shirt sizing. So let's say you're a t-shirt manufacturer, and what you've done is you've gone to the population that you want to sell t-shirts to, and you've collected a number of examples of the height and weight of these people in your population. So and I guess height and weight tend to be positively correlated, and so maybe you end up with a data set like this, with a sample, with a set of examples of different people's heights and weight. Let's say you want to size your t-shirts. Let's say I want to design and sell t-shirts of 3 sizes: small, medium, and large. So how big should I make my small, and how big should I make my medium, and how big should I make my large t-shirts? One way to do this would be to run the k-means clustering algorithm on this data set that I have shown on the right. And maybe what k-means will do is group all of these points into one cluster, and group all of these points into a second cluster, and group all of those points into a third cluster. So even though the data, beforehand it didn't seem like we have 3 well-separated clusters, k-means will kind of separate separate out the data into multiple clusters for you. And what you can do is then look at this first population of people, and look at them, and look at the height and weight, and try to design a small t-shirt so that it kind of fits this first population of people well, and then design a medium t-shirt and design a large t-shirt. And this is in fact kind of an example of market segmentation, where you're using k-means to separate your market into 3 different segments, so you can design a product separately, that is the small, medium, and large t-shirts, that tries to suit the needs of each of your 3 separate subpopulations well. So that's the k-means algorithm, and by now you should know how to implement the k-means algorithm and kind of get it to work for some problems. But in the next few videos, what I want to do is really get more deeply into the nuts and bolts of k-means, and talk a bit about how to actually get this to work really well.
The quantum computer. These are the worst exercises for men over 50. Number 1, running on.
Most of the supervised learning algorithms we've seen, things like linear regression, logistic regression, and so.
So here we will talk about optimization of k-means, clustering optimization.
All of those algorithms had an optimization objective, or some cost function that the algorithm was trying to minimize. It turns out that k-means also has an optimization objective, or a cost function that is trying to minimize. And in this video, I'd like to tell you what that optimization objective is. And the reason I want to do so is because this will be useful to us for 2 purposes. First, knowing what is the optimization objective of k-means will help us to debug the learning algorithm and just make sure that k-means is running correctly. And second, and perhaps even more importantly, in a later video, we'll talk about how we can use this to help k-means find better clusters and avoid local optima. But we'll do that in a later video that follows this one. Just as a quick reminder, while k-means is running, we're going to be keeping track of 2 sets of variables. First is these CIs, and that keeps track of the index, or the number of the cluster to which an example xi is currently assigned. And then the other set of variables we use is mu subscript k, which is the location of cluster centroid k. And again, for k-means, we use capital K to denote the total number of clusters, and here lowercase k, is going to be an index into the cluster centroids, and so lowercase k is going to be a number between 1 and capital K. Now, here's one more bit of notation, which is going to use mu subscript ci to denote the cluster centroid of the cluster to which example xi has been assigned, right? And here's to explain that notation a little bit more. Let's say that xi has been assigned to cluster number 5. What that means is that ci, that is the index of xi, that is equal to 5, right? Because having ci equals 5, that's what it means for the example xi to be assigned to cluster number 5. And so mu subscript ci is going to be equal to mu subscript 5, because ci is equal to 5. And so this mu subscript ci is the cluster centroid of cluster number 5, which is the cluster to which my example xi has been assigned. Armed with this notation, we're now ready to write out what is the optimization objective of the k-means clustering algorithm. And here it is. The cost function that k-means is minimizing is a function j of all of these parameters, C1 through Cm and mu1 through mu k, that k-means is varying as the algorithm runs. And the optimization objective is shown on the right is the average, or 1 over m, of sum from I equals 1 through m of this term here that I've just drawn the red box around, right, of the squared distance between each example xi and the location of the cluster centroid to which xi has been assigned. So let me just draw this in, let me just explain this, right? So here's the location of training example xi, and here's the location of the cluster centroid to which example xi has been assigned. So to explain this in pictures, if here's x1, x2, and if a point here is my example xi, so if that is equal to my example xi, and if xi has been assigned to some cluster centroid, I'm going to denote my cluster centroid with a cross. So if that's the location of, mu 5, let's say, if xi has been assigned to cluster centroid 5, as in my example up there, then this squared distance, that's the squared of the distance between the point xi and this cluster centroid to which xi has been assigned. And what k-means can be shown to be doing is that it is trying to find parameters ci and mu I, trying to find c and mu to try to minimize this cost function j. This cost function is sometimes also called the distortion cost function, or the distortion of the k-means algorithm. And just to provide a little bit more detail, here's the k-means algorithm. Here's exactly the algorithm as we have written it out on the earlier slide. And what this first step of this algorithm is, this was the cluster assignment step, where we assign each point to the cluster centroid. And it's possible to show mathematically that what the cluster assignment step is doing is exactly minimizing j, with respect to the variables c1, c2, and so on up to cm, while holding the cluster centroids mu1 up to mu k fixed. So what the cluster assignment step does is, it doesn't change the cluster centroids, but what it's doing is exactly picking the values of c1, c2 up to cm that minimizes the cost function, or the distortion function j. And it's possible to prove that mathematically, but I won't do so here. But it has a pretty intuitive meaning of just, let's assign each point to the cluster centroid that is closest to it, because that's what minimizes the squared distance between the point and its corresponding cluster centroid. And then the other part of the second step of k-means.
Before starting with the second step of the algorithm, here how we optimize k-mean, by minimizing the distance between the data point and the centroids, which means that this data point is, we are almost accurate that it's belong to this cluster. This is how we optimize mathematically the data point to be belong to a certain cluster. Clear? This is the first step when we optimize the k-means algorithm. At the first step, cluster assignment step. So we try to optimize it. We minimize the j with respect to c1, c2, c3, which is the cluster assignment, that this data point belongs to this cluster. The second step, which is take the average or the mean of the current cluster and data points to give a new mu or a new centroid value. Then we will repeat the step until it converges.
This second step over here, the second step was the move centroid step. And once again, I won't prove it, but it can be shown mathematically that what the move centroid step does is it chooses the values of mu that minimizes j. So it minimizes the cost function j with respect to, WRT is my abbreviation for with respect to, but it minimizes j with respect to the locations of the cluster centroids mu1 through mu capital K. So what k-means really is doing is just taking the two sets of variables and partitioning them into two halves, right? You have first the c sets of variables, and then you have the mu sets of variables. And what it does is it first minimizes j with respect to the variable c, and then minimizes j with respect to the variables mu, and then it keeps on iterating. And so that's all that k-means does. And now that we understand k-means as trying to minimize this cost function j, we can also use this to try to debug our learning algorithm and just kind of make sure that our implementation of k-means is running correctly. So we now understand the k-means algorithm as trying to optimize this cost function j, which is also called the distortion function. We can use that to debug k-means and help make sure that k-means is converging and is running properly. And in the next video, we'll also see how we can use this to help k-means find better clusters and help k-means to avoid local optima. In this video, I'd like to talk about how to initialize.
So as you see, what Andrew and G said, that we're trying to find the local optima, not a global optima, because we are not sure with current clustering and the optimization that we reach to global minimum. And I believe during the optimization lectures, we talk about what do we mean by local optimum and global optimum. Global, it is the minimum point that we can achieve. We are sure that the optimization function converge at global, which is the lowest value that we could achieve. However, with the clustering, we are not sure it's a global. That's why we are talking it's the global minimum of the current cluster. Guys, these points and comments are very important. Okay, let's continue.
K-means, and more importantly, this will lead into a discussion of how to make k-means avoid local optima as well. Here's the k-means clustering algorithm that we talked about earlier. One step that we never really talked much about was this step of how you randomly initialize the cluster centroids. There are a few different ways that one could imagine using to randomly initialize the cluster centroids, but it turns out that there's one method that's much more recommended than most of the other options one might think about. So let me tell you about that option, since it's what often seems to work best. Here's how I usually initialize my cluster centroids. When running k-means, you should have the number of cluster centroids k set to be less than the number of training examples m. It would be really weird to run k-means with a number of cluster centroids that's equal or greater than the number of examples you have, right? So the way I usually initialize k-means is I would randomly pick k training examples. So, and what I do is then set mu1 up to mu k equal to these k examples. Let me show you a concrete example. Let's say that k is equal to 2, and so on this example on the right, let's say I want to find 2 clusters. So what I'm going to do in order to initialize my cluster centroids is I'm going to randomly pick a couple examples, and let's say I pick this one and I pick that one. And the way I'm going to initialize my cluster centroids is I'm just going to initialize my cluster centroids to be right on top of those examples. So that's my first cluster centroid, and that's my second cluster centroid, and that's one sort of random initialization of k-means. The one I drew looks like a particularly good one. Sometimes I might get less lucky, and maybe I'll end up picking that as my first randomly chosen example, and that as my second one. And here I'm picking 2 examples because k equals 2. So I'm going to randomly pick 2 training examples. And if I chose those 2, then I'll end up with maybe this as my first cluster centroid, and that as my second initial location of the cluster centroid. So that's how you can randomly initialize the cluster centroids. And so at initialization, your first cluster centroid mu1 will be equal to xi for some randomly value of I, and mu2 will be equal to xj for some different randomly chosen value of j, and so on if you have more clusters and more cluster centroids. As sort of a side comment, I should say that in the earlier video where I first illustrated k-means with an animation, in that set of slides, only for the purpose of illustration, I actually used a different method of initialization for my cluster centroids. But the method described on this slide, this is really the recommended way and the way that you should probably use when you implement k-means. So as is suggested perhaps by these two illustrations on the right, you might really guess that k-means can end up converging to different solutions depending on exactly how the clusters were initialized. And so depending on the random initialization, k-means can end up at different solutions. And in particular, k-means can actually end up at local optima. If you're given a data set like this, well, it looks like, there are 3 clusters. And so if you run k-means and if it ends up at a good local optima, this might be really the global optimum, you might end up with that clustering. But if you had a particularly unlucky random initialization, k-means can also get stuck at different local optima. So in this example on the left, it looks like the blue cluster has captured a lot of points on the left, and then the red and the green clusters each is capturing only a relatively small number of points. And so this corresponds to a bad local optima because it has basically taken these 2 clusters and merged them into one, and furthermore, it has split the second cluster into 2 separate subclusters like so. And it has also taken the second cluster and split it into 2 separate subclusters like so. And so both of these examples on the lower right correspond to different local optima of k-means. And in fact, in this example here, the red cluster has captured only a single unlabeled example. And the term local optima, by the way, refers to local optima of this distortion function J. And what these solutions on the lower left, what these local optima correspond to is really solutions where k-means has gotten stuck at the local optima and is not doing a very good job minimizing this distortion function J. So if you're worried about k-means getting stuck in local optima, if you want to increase the odds of k-means finding the best possible clustering like that shown on top here, what we can do is try multiple random initializations. So instead of just initializing k-means once and hoping that that works, what we can do is initialize k-means lots of times and run k-means lots of times and use that to try to make sure we get as good a solution, as good a local or global optimum as possible. Concretely, here's how you could go about doing that. Let's say I decide to run k-means 100 times. So I'm going to execute this loop 100 times. And a fairly typical number of times to run k-means would be something from 50 up to maybe 1,000. So, but let's say you decide to run k-means 100 times. So what that means is we would randomly initialize k-means, and for each of these sort of 100 random initializations, we would run k-means, and that would give us a set of clusterings and a set of cluster centroids. And we would then compute the distortion J, that is compute this cost function, on the set of cluster assignments and cluster centroids that we got. Finally, having done this whole procedure 100 times, you will have 100 different ways of clustering the data. And then finally, what you do is, out of these 100 ways we've found of clustering the data, just pick one that gives us the lowest cost, that gives us the lowest distortion. And it turns out that if you're running k-means with a fairly small number of clusters, so if the number of clusters is anywhere from 2 up to maybe 10, then doing multiple random initializations can sometimes make sure that you find a better local optimum, make sure that you find a better clustering of the data. But if k is very large, so if k is much greater than 10, certainly if k were, if you're trying to find hundreds of clusters, then having multiple random initializations is less likely to make a huge difference, and there's a much higher chance that your first random initialization will give you a pretty decent solution already, and doing multiple random initializations will probably give you a slightly better solution, but maybe not that much. But it's really in the regime of when you have a relatively small number of clusters, especially if you have maybe 2 or 3 or 4 clusters, that random initialization could make a huge difference in terms of making sure you do a good job minimizing the distortion function and giving you a good clustering. So that's k-means with random initialization. If you're trying to learn a clustering with a relatively small number of clusters, 2, 3, 4, 5, maybe 6, 7, using multiple random initializations can sometimes help you find much better clusterings of the data. But even if you're learning a large number of clusters, the initialization, the random initialization method that I describe here, that should give k-means a reasonable starting point to start from for finding a good set of clusters. In this video, I'd like to talk about one last detail of k-means clustering, which is how to choose the number of clusters, or how to choose the value of the parameter capital K. To be honest, there actually isn't a great way of answering this or of doing this automatically, and by far the most common way of choosing the number of clusters is still choosing it manually by looking at visualizations or by looking at the output of the clustering algorithm or something else. But I do get asked this question quite a lot of how do you choose the number of clusters, and so just want to tell you, what are people's current thinking on it, although the most common thing is actually to choose the number of clusters by hand. A large part of why it might not always be easy to choose the number of clusters is that it's often genuinely ambiguous how many clusters there are in the data. Looking at this data set, some of you may see 4 clusters, and that would suggest using k equals 4, or some of you may see 2 clusters, and that will suggest k equals 2, and yet others may see 3 clusters. And so looking at the data set like this, the true number of clusters, it actually seems genuinely ambiguous to me, and I don't think there is one right answer. And this is part of unsupervised learning. We aren't given labels, and so there isn't always a clear-cut answer. And this is one of the things that makes it more difficult to, say, have an automatic algorithm for choosing how many clusters to have. When people talk about ways of choosing the number of clusters, one method that people sometimes talk about is something called the elbow method. Let me just tell you a little bit about that and then mention some of its advantages but also shortcomings. So the elbow method, what we're going to do is vary k, which is the total number of clusters. So we're going to run k-means with one cluster. That means really everything gets grouped into a single cluster, and compute the cost function, or compute the distortion j, and plot that here. And then we're going to run k-means with 2 clusters, maybe with multiple random initializations, maybe not. But then, with 2 clusters, we should get hopefully a smaller distortion, so plot that there. And then run k-means with 3 clusters. Hopefully you get an even smaller for the distortion, and plot that there. And run k-means with 4, 5, and so on. So we end up with a curve showing how the distortion goes down as we increase the number of clusters. And so we get a curve that maybe looks like this. And if you look at this curve, what the elbow method does is it says, well, let's look at this plot. Looks like there's a clear elbow there, right? This is maybe by analogy to the human arm, where if you imagine that you reach out your arm, then this is your shoulder joint, this is your elbow joint, and I guess your hand is at the end over here. Right? And so this is the elbow method, and you find this sort of pattern where the distortion goes down rapidly from 1 to 2 and 2 to 3, and then you reach an elbow at 3, and then the distortion goes down very slowly after that. Then it looks like, maybe using 3 clusters is the right number of clusters, because that's the elbow of this curve, right? That it goes down, distortion goes down rapidly until k equals 3, then it goes down very slowly after that, so let's pick k equals 3. If you apply the elbow method and if you get a plot that actually looks like this, then that's pretty good, and this would be a reasonable way of choosing the number of clusters. It turns out the elbow method isn't used that often, and one reason is that if you actually use this on a clustering problem, it turns out that fairly often, you end up with a curve that looks much more ambiguous, of maybe something like this. And if you look at this, I don't know, maybe there's no clear elbow, right? It looks like distortion continuously goes down. Maybe 3 is a good number, maybe 4 is a good number, maybe 5 is also not bad. And so if you actually do this in practice, if your plot looks like the one on the left, then that's great, gives you a clear answer. But just as often, you end up with a plot that looks like the one on the right, and is not clear what where the location of the elbow is. It makes it harder to choose a number of clusters using this method. So maybe the quick summary of the elbow method is that it's worth a shot, but I wouldn't necessarily, have a very high expectation of it working for any particular problem. Finally, here's one other way of how thinking about how you choose the value of k. Very often, people are running k-means in order to get clusters for some later purpose or for some sort of downstream purpose. Maybe you want to use k-means in order to do market segmentation, like in the t-shirt sizing example that we talked about. Maybe you want k-means to organize a computer cluster better, or maybe a learning cluster for some different purpose. And so if that later downstream purpose, such as market segmentation, if that gives you an evaluation metric, then often a better way to determine the number of clusters is to see how well different numbers of clusters serve that later downstream purpose. Let me step through a specific example. Let's say we go through the t-shirt sizing example again, and I'm trying to decide, do I want 3 t-shirt sizes? So if I choose k equals 3, then I might have small, medium, and large t-shirts. Or maybe I want to choose k equals 5, and then I might have extra small, medium, large, and extra large t-shirt sizes. So you can have like 3 t-shirt sizes or 4 or 5 t-shirt sizes. We could also have 4 t-shirt sizes, but I'm just showing 3 and 5, just to simplify this slide for now. So if I run k-means with k equals 3, maybe I end up with that's my small, and that's my medium, and that's my large. Whereas if I run k-means with 5 clusters, maybe I end up with, those are my extra small t-shirts, these are my small, these are my medium, these are my large, and these are my extra large. And the nice thing about this example is that this then maybe gives us another way to choose whether we want 3 or 4 or 5 clusters. And in particular, what you can do is, think about this from the perspective of the t-shirt business and ask, well, if I have 5 segments, then how well will my t-shirts fit my customers? And so how many t-shirts can I sell? How happy will my customers be? What really makes sense from the perspective of the t-shirt business in terms of whether I want to have more t-shirt sizes so that my t-shirts fit my customers better, or do I want to have fewer t-shirt sizes so that I make fewer sizes of t-shirts and I can sell them to the customers more cheaply? And so it's the t-shirt selling business that might give you a way to decide between 3 clusters versus 5 clusters. So that gives you an example of how a later downstream purpose, like the problem of deciding what t-shirts to manufacture, how that can give you an evaluation metric for choosing the number of clusters. For those of you that are doing the programming exercises, if you look at this week's programming exercise associated with k-means, there's an example there of using k-means for image compression. And so if you were trying to choose how many clusters to use for that problem, you could also, again, use the evaluation metric of image compression to choose the number of clusters k. So how good do you want the image to look versus how much do you want to compress the file size of the images. And if you do the programming exercise, what I just said will make more sense at that time. So just to summarize, for the most part, the number of clusters k is still chosen by hand by human input or human insight. One way to try to do so is to use the elbow method, but I wouldn't always expect that to work well. But I think the better way to think about how to choose the number of clusters is to ask, for what purpose are you running k-means, and then to think what is the number of clusters k that serves that whatever later purpose that you're actually running k-means for.
Question: would you build a website for a major brand with more than 200 million users?
In this video, I'd like to start talking.
Okay, guys, we're done with clustering algorithm, the k-means, how we optimize it, how we choose the best number for k's, which means the best number for clusters. We understand how the algorithm, it's work in 2 steps. The first one is a cluster assignment, then the other one, calculate the new average of the centroid. Now we will back to the dimensionality reduction. However, now we'll talk about the expectation maximization algorithm, clustering algorithm, and the mixture clustering models. The link for the new series is available in OWL at your course website. So it's here in the resources. Mixture model. Where it is it? Maybe this one. No,
In this and the next few videos.
Logistic regression. Yes, here. So this is the handout. These are the handout that will be discussed. Where is the video link? Yes, here.
And we fit the Gaussians now. So we'll talk about mixture models and the expectation maximization algorithm. One way to think of EM, one way to think of mixture models is in relation to the clustering methods. Remember, we had classification of different clustering methods. Some of them are hard boundaries, so element either goes into the cluster or doesn't. And I said that some clustering methods are soft, right? So that's where an element kind of belongs to multiple clusters at the same time, but with different degree of belief, right? It can have say a confidence of 60% in cluster 1 or 40% in cluster 2, but it can be in 2 simultaneously. So mixture models are basically a probabilistically sound way of doing soft clustering. And what you do in mixture models, in Gaussian mixtures, which we're going to cover, is each cluster corresponds to a generative model. It corresponds to a probability distribution. So that's typically a Gaussian or a multinomial, and we're going to run through a Gaussian example because we're looking for real values. So each cluster basically corresponds to a probability distribution, and what you want to discover as part of the EM algorithm are the parameters of the probability distribution. So that would be the mean and the covariance of each Gaussian. If you have a Gaussian, or for a multinomial, it would be the probabilities for each outcome of the random variable. And the EM algorithm is what allows you to infer those parameter values. So let's look at the problem with a small example. Right? Suppose I have a bunch of data points like that, and I know that these two.
Here, guys, he's tried to use the Gaussian model for mixture model with linear data, which mean one-dimensional data.
Data points come from two sources. They come from two models, right? So these guys come from the yellow source, and these guys come from the blue source. Now, if I know that there are two sources, and I assume that the sources are Gaussian, it's a one-dimensional task. The only thing that I need to do for a one-dimensional Gaussian is estimate the mean and estimate the variance, right? So, do we know how to do that? Yeah, it's pretty easy. Why? Because we know which points came from which Gaussian. So, say for the blue Gaussian, I have 1, 2, 3, 4, 5 data points that came from it. So all I need to do is I just need to take their x values, add them up, divide them by 5, and that's going to give the mean. That's going to give me an estimate of the mean of the blue Gaussian, right? And the same thing for the variance. I take their x values, subtract from them the blue mean. By the way, that should not be mu1, that should be mu of b, the blue mean, and that's the blue mean as well. Right? You always subtract the same thing. So you take the squared deviations from the blue mean, average them out, and that is your estimate for the variance of that Gaussian. So I can do it for the blue, I can do it for the yellow, and lo and behold, I'll get my estimates of the two Gaussians. Now, this is great. We know how to do this. We did this in the first lecture. And this is based on knowing which point came from which distribution. So what if you have that? Right? What if you have just a bunch of data points? You don't know which one of them came from the yellow, which one of them came from the blue. can we fit the Gaussians now? Well, that's a lot trickier, isn't it? Right? Because we don't know, now we don't know which ones go where. Right? We don't know which ones came from the blue, which ones came from the yellow. And this is the situation that you have when you're doing mixture models. You have a bunch of data points and you suspect that they came from k different Gaussians, but you have no idea which points came from which Gaussian. Right? So you're going to fit the parameters, but you don't know which point came from where, and that makes it hard. Now, if we happened to know the parameters of the Gaussian, right? So if somebody came along and told us that the blue Gaussian has a certain mean and variance, and the yellow Gaussian has a certain mean and variance, right? So if we knew where the Gaussians were, we could actually figure out which point is likely from which Gaussian, right? Because for each point, we could compute, well, what is the probability of that point coming from the yellow Gaussian? Is that going to be big or small? Big, right? It's right on the mean, right? What's the probability that it came from the blue? Small. So this point very likely came from the yellow Gaussian and not the blue Gaussian. So if somebody came along and told you the parameters, here are the means, here are the variances, you could work out which point came from which Gaussian. And the way you would do that is just using the Bayes rule and the Gaussian formula, right? So the probability that a certain point xi is blue, use Bayes rule, and for the generative probability, you just stick them to the Gaussian. Take the point xi, subtract from it the blue mean, square it, divide it by 2 of blue variances, exponentiate it, and there you have a number. Right. So, and in this case, what you would expect is these points are probably more likely to be blue, and these points are more likely to be yellow. So what you have is you have a bit of a chicken and egg problem, right? If somebody told you which points came from which source, you could estimate the means and variances trivially. But nobody tells you which point came from where. Now, if you had the parameters, if you knew the means and the variances, you could figure out which point came from which distribution. But again, you don't have that, right? So you need one to estimate the other and the other to estimate the one. And that's what the EM algorithm basically does for you. The way it works is it's going to start by placing the Gaussians randomly in space somewhere, right? Much like the k-means algorithm. So it's going to come up with a random mean and the random variance. And then what it's going to do is for each point xi, it's going to try to figure out, with these current parameters, does this xi look like it came from the yellow or the blue Gaussian? And it's going to assign them to the yellow or blue, but unlike k-means, it's not going to do a hard assignment. So k-means takes a point and puts it into one cluster or the other. EM computes the probability that it goes into the blue cluster or the yellow, and it never quantizes that probability. It never sets it to 0 or 1. It just keeps it as a number between 0 and 1. Right? So that's why it's soft clustering. It doesn't assign a point. It says, here's the probability that it came from this distribution, and here's the probability that it came from that distribution. Okay? Now, once it has computed these assignments, the probability that it came from the blue, it's going to use those numbers to re-estimate the means and the variances to fit the point assignments a little bit better. So that part is very much like k-means. The part that's different is that you're using probabilities here. Right. And then, just like k-means, you keep iterating this until it converges.
At Synity, we understand better than anyone that having an accurate 360-degree...
So let's look at an example in 1D. So we start with a bunch of points, one-dimensional points. We don't have any labels for them. So the only thing we know is that they came from two Gaussians, and we want to discover what these two Gaussians are automagically. The way we're going to do that is we're going to start by placing two Gaussians in a random sort of in random positions on the line, and these are one-dimensional Gaussians, so their mean is just a number. So here's the mean for the yellow, here's the mean for the blue, and they have the same variance in this case. So the first step of the algorithm, we're going to figure out how likely is each of the points to come from the yellow or from the blue. So basically, for each one of these points, we're asking a question: does it look more like the yellow like a sample from the yellow Gaussian, or a sample from the blue Gaussian? And the way we compute that is using Bayes' rule. So that's a generative probability. You take xi, subtract the mean of the blue Gaussian, square it, divide by the variance, exponentiate, normalize. That gives you the probability that that point xi came from the blue Gaussian. Right. So let's pick a point. That point right there. Right. The rightmost point. Will it have a high probability Pxi given B? No. It's going to be very, very small, because that point is very far from the blue mean, and the blue variance is kind of spiky. It's not very spread out. Right? Will it have a high number for the yellow? It'll be even smaller. Right? And that's where interesting things start to happen. So this will have a small number for blue, but the number for yellow is going to be much, much smaller, orders of magnitude smaller. So then, when you compute the Bayesian posterior, you take both of those probabilities from the blue and from the yellow, you combine them with the priors. By the way, assume priors are equal for now. Stick them in the Bayes rule. Bi for that point is going to come out to be almost 1. That point doesn't look like a sample from the blue, it doesn't look like a sample from the yellow, but it's much more, I guess it's much more unlike the yellow than it is unlike the blue. So the posterior is actually going to be really high for that point. It's going to be assigned to the blue. And that's just Bi for one point, and of course you would repeat it for all of them, right? So for example, this point, would you expect Bi to be high or low? It's a probability that that point came from the blue. Well, no, actually, it should be pretty low, right? So this is very, very close to the yellow mean, and it's a lot further away from the blue mean, right? So that point is going to be mostly yellow with a little bit of a probability for the blue. This one is going to be mostly blue with maybe a tiny bit of the yellow, and all of these are going to be blue pretty much throughout. So you compute the BIs, you compute the AIs, which are just 1 minus BI, so that's the probability that they came from the yellow. And then these numbers, the BIs, they basically represent a coloring of the points. Again, it's just like k-means, only in k-means, points would be either colored fully blue or fully yellow, and here we have sort of fractional colorings, right? This one is mostly yellow, this one is mostly blue, these ones are pretty much entirely blue, but you have a bit of a mixture, right? So the point belongs to both the yellow and the blue distributions. And once I've done the coloring, I can do re-estimation, right? I can now take these colors and say, well, these points, they came from the blue, so now I can estimate the blue mean and the blue variance, because now I've got the assignments, right? And the way you do that is really simple. You just add up the x's for the points and you divide by this sum. Now, this sum is a little bit odd, and the first time you see it, it's going to look a little bit confusing. So what you're doing is you're taking each x value, x1, x2, and so on, you're multiplying it by bi, which is the posterior, and you're adding them up. Now, if you're having a hard time understanding what you're doing here, pretend for a moment that you're doing k-means instead of em. If you were doing k-means, these bi's would be 0 or 1. The point either goes into the blue cluster or it goes into the yellow cluster. So bi is 1 if the point goes into blue cluster, and it's 0 if it goes into the yellow, right? So if that happens, suppose that that point bi was 0, and for everything else bi was 1, right? So what does that look like now? b1 is 0, so x1 is not a part of this sum, and B1 is not a part of the bottom either. Now what's left? B2 would be 1, B3 would be 1, all of them would be 1. So what you're doing is you're taking all the points except the first point and adding up their x values and dividing by the number of the points that went to the blue cluster. That's just n minus 1 in this case, right? So your estimation is the same as if somebody came in and told you, these are the points from the blue cluster, right? Does this make sense? This is actually the critical thing. If you get this, you'll get the rest of it. This is good. Is everyone good on this? Okay. So that's how you re-estimate the blue mean. The difference now is BIs are not just 0 and 1, they're probabilities, they're numbers between 0 and 1. So what it means is when you're computing the blue mean, these points, xn minus 1, they get the full weight, they give their full weight to the blue mean, and the point x1 gives a tiny fraction of its weight to the blue mean, and it's going to give a bigger fraction of its weight to the yellow mean. So that's the soft assignments for you. It basically, in k-means, a point contributes either to one centroid or to another. In EM, a point gives a little bit of its mass to every centroid, but it gives more mass to the centroids that it's more associated with. So that's what those BIs represent. And of course, you compute the variance in the same way. You take the deviations from this mean that you've computed, and again, this is not mu1. I'm sorry about the bug on the slide. This should be the mu of b, and this should be the mu of b as well. So you take the difference between each x and the mean for the blue mean, right? And you multiply those squared differences by the weights, by the confidences that that point is from the blue distribution or from the yellow distribution. So this is for the blue, and then you do the same thing for the yellow, right? So you multiply the numbers by the AIs, which are the weights, the probability that the point is associated with a yellow distribution. And you do the same thing for the mean and for the variance. And I guess just remember that AIs are just 1 minus BI. So in this formula for AI, which term is going to dominate at the first iteration? First. Yeah. So there's only really one point that's going to dominate. All of these AIs are going to be very, very small because most points are colored blue. The only one that's colored mostly yellow is that one. So there's going to be lots of weight on this point. Sorry about the pointer. And there's going to be a little bit of weight on the second point, and there's going to be 0 weight on everything else. Okay? So when you do that, that is going to be the likely result. So your yellow Gaussian is going to pretty much stay where it was. It's going to move a little bit because it's all concentrated on one point, on that one point with a little bit of contribution from that point. But your blue Gaussian is going to move massively to the right because now all of these blue points are pulling on it. So they participate in the recomputation of the mean and the variance. So it's going to pull the Gaussian, they're going to pull the Gaussian towards them. And that's one iteration of EM. And of course you don't stop here, you keep going. So at the next iteration, you're going to redo the coloring, and now the coloring is going to be a little bit different. So those points are going to pull a lot more on the blue Gaussian, so it's probably going to migrate to these points, and the yellow is going to start encroaching on its turf. And eventually, after a few iterations, it might look something like that. Right? So this is a made-up example, but this is what it might end up looking like. So that's essentially how you estimate the means and the variances starting from nothing. Just a set of data points. I only estimated the parameters of the Gaussians. I didn't estimate the priors. I kept the priors uniform. But you can also estimate the priors. So the way you would do that is the prior for the blue, you just add up all of the BIs and divide them by the number of data points that you have, and that is the estimate for how. Basically, what this is telling you is it's telling you what proportion of the points is the blue distribution describing now? What proportion of the data is it describing? If you do that, you actually have to be careful because a lot of the time, in a case like that, after the first iteration, blue would grab everything, right? And then yellow might get zeroed out. So that happens commonly. So sometimes you just peg the priors at equal at a uniform distribution. So you force them to be 0.5 and you don't re-estimate them. Okay, so that was that example was in one dimension, and generalizing it to more than one dimension isn't terribly hard. It's just the examples don't look as nice. So when you have k dimension, when you have d dimensions. The assumptions are the same. You have data. Each data instance has d attributes. They come from k sources or distributions. So in 2D, it might look something like that, right? That's what I want to get. I get a bunch of data points, and I want to fit two Gaussians to them. Each of my sources is Gaussian, and you estimate the parameters very much in the same way that we did for 1D, only now you do it a little bit more generally. So priors, you just count. So for a particular source C, you take the posterior distributions. Those are our BIs from the previous slide. You add them up, divide by n, and that gives you the prior for one of the Gaussians, for the Cth Gaussian. The mean of the Gaussian becomes the expected value of the attribute across all the items weighted by this posterior. So it's going to look something like that. You're going to sum up over all data points. Xij, that's the value of the jth attribute in the ith example. And this is our BI divided by the sum of the BIs. Right? That's the weight, how much xi is associated with Gaussian number C. Covariance, so in the 1D case, you only have variance, right, because it's one-dimensional. As soon as you have 2 dimensions, then you talk about covariance. Covariance, so you have 2 attributes, j and k, and for the Cth Gaussian, the covariance is just that expression, right? So you take the difference for the ith data item, the difference between the jth attribute value and its mean, the kth attribute value and its mean, multiply them together, and again multiply by the same factor. This is our BI. This is how much the point is associated with the Cth Gaussian. And all of these require you to have these posteriors, right? All of the estimation is based on the posteriors, and the way you compute the posteriors is just using Bayes' rule. So that's Bayes' rule, and the way you compute these components is just with a with a d-dimensional Gaussian. So you take the ith data instance, subtract the mean for the Cth Gaussian. So that's a vector, and here you insert the inverse of the covariance matrix into it and just exponentiate it, normalize. So that's what you do in more than one dimension. But really, so make sure that you understand the 1D example, and then this is going to become really, really straightforward. I'll stop here. We'll pick up on the next lecture. Thanks. All right, so last time we were talking about the Gaussian mixture models in the EM algorithm, and we ran through an example in 1D, and the basic idea there is you've got a bunch of points. You want to fit 2 Gaussians to these points. You don't know which point came from which Gaussian, so what you do is you place the Gaussians randomly somewhere in the space, use these positions to figure out which point looks like which Gaussian, and then use those assignments to re-estimate the positions of the Gaussian, and just repeat that until convergence. So that's the 1D example, and we left off on the multiple dimensions. And in k dimensions or in d dimensions, you basically do the same thing, only equations become a tiny bit more complicated. Now, instead of a single number, you have vectors, and you're doing everything over vectors, right? So each source is still a Gaussian, and what you're doing is to do the mean. So the mean vector is going to be the average of all the instance vectors weighted by the probability that that instance came from Gaussian C, from the source C, right? And you do it for each attribute J in your set of in your set of attributes. So that's what you do for the mean. You can also estimate variances, but if your dimensionality is not too huge, you can also estimate covariances. And covariances allow you to have Gaussians that are not aligned to the axes. They allow you to estimate Gaussians that are oblique. So for example, this red Gaussian, you see how it's not sort of flat, it's tilted, and the blue one is tilted as well. To have a Gaussian that looks like that, you need a covariance matrix. So you need to encode how each attribute, how the attributes influence each other, right? How they correlate. And that's encoded by the covariance matrix. And the way you compute the covariance matrix is for a pair of attributes J and K, you look at each instance I, xi, and you see how far was the jth attribute away from the mean, how far was the kth attribute away from the mean, multiply them together, and add it up over all data points weighted by the probability that that data point came from the Cth Gaussian, right? Because you're updating the Cth covariance matrix. So that basically tells you, are the attributes positively correlated or negatively correlated? So as one increases, does the other decrease or increase? And for all of those, you need the weight. And the weight is just the probability that the ith data point came from the Cth Gaussian in the mixture, and you get that with a Bayes rule, and it's based on the normal distribution, right? So and that's what the inverse, that's what the Gaussian looks like for multiple dimensions, right? Rather than single attributes, you now have vectors. So you have a vector difference between the ith instance and the mean for the Cth Gaussian. Again, the same vector, and you multiply them together, but you insert the inverse of the covariance matrix in the middle. So that's what it looks like. Okay, great. You'll notice that from the start, just like in k-means, we decide how many Gaussians we're going to be fitting. Just like k-means, we said that we're going to have, say, 2 clusters or 10 clusters. Here you need to do the same thing. And in many cases, you might want to sort of discover, well, how many Gaussians are enough? How many should I be using? Should I be using 10? Should I be using 1,000? What's the right number for my data set? And the answer here is not much more clear than for k-means. You have slightly different methods, slightly more powerful methods, and that's because Gaussian mixtures and EM in general, it's a probabilistic model, so you have a better defined objective function. So when you're fitting a mixture model, what you're trying to do is you're trying to maximize the likelihood or the log likelihood of your data under the assumption that it's generated from a mixture model. So you have a mixture of k components, and what you're doing is you're effectively measuring what's the probability that each instance xi came from the kth component multiplied by the prior for that component, add it all up, so that's the total probability for xi, and then add or multiply them together or add their logs over all the instances that you have. So that's a log likelihood of the data, assuming that it came from those Gaussians. So now what you could try to do is you could try to say, well, I want to maximize the likelihood. I want to make this likelihood as large as it can possibly get, because that indicates if the likelihood is large, this means that my model, my mixture of Gaussians, fits the data well. So you could try to use that directly to maximize k, basically run it with different values of k and then see which one gives you the best result. The problem, though, is that this is going to be maximized when each instance has its own little Gaussian dedicated to it. So that's the same argument that we had in k-means. So the highest likelihood you can get is when for each data point there is a separate little Gaussian sitting on top of that data point and giving it a high probability mass. So that's when you're going to get a high likelihood, and of course that's not a very useful mixture. So you maybe want to come up with something better. You could try to use a training set and a validation set. So this would measure how well does this mixture generalize to new data that I'm going to see tomorrow. And in some domains this will work, but for many other domains you're still going to get best result when k, the number of components in the mixture, is very, very large. So maybe n, which is the number of training instances in your training set. So if you use this directly, you're still going to end up with with a mixture model that has lots and lots of Gaussians, many more than you would like to have. So how do you get around this? If you're following the book advocates a couple of metrics here. So they're sensible metrics. They have a nice interpretation. In practice, how well they work in practice is sort of a different question. So the interpretation, the intuition that you want to use here is that of the Occam's razor, right? So Occam's razor says that if you got a bunch of data, and you have multiple hypotheses that could explain what's happening in your data, you should pick the simplest possible explanation. Right? So the idea is, you can have a complicated explanation for something, you can have a simple explanation for something. If they both explain it equally well, you should go for the simpler one, because it's less likely to go wrong somewhere in the details. So, keep it simple in a way.
Okay, guys, here in the mixture models, or how many Gaussian that we'll pick, if we are following the probabilistic model, then we'll take the L equal logarithm P from x1 to xn, which is the features, sigma from I equal 1 to n, logarithm sigma from k equal 1 to k capital, probability of xi over k for p of k. Now here I need you to just make sure that when we saying L, which means the likelihood function, how will our model fit the data? If we are using p, small p, then p is the number of parameters, which imply how simple is our model. Okay, these things, the probabilistic model, pick k that makes L as large as possible, split points into training set T and validation set V. Here we are using the principle of cross-validation. We'll talk about it maybe next week. Occam's razor, then we pick the simplest of all models that fit if we are using the Bayes or the other model by maximizing P or minimizing P. Let's continue.
There are two ways to encode it. So a Kaiki information criterion, basically what you're doing here is you're trying to define simple in terms of mixture models. So now it has two parts, P and L. So P is a measure of how simple the model is, and the way you compute it is you look at the total number of parameters that your model has. Now, so let's think about a simple example, one-dimensional Gaussian, right? Let's say I'm fitting two one-dimensional Gaussians. How many parameters do I have? Nope. So 4, 6. It's actually 5. It's in the middle. So I have the mean for each Gaussian, right? I have the variance for each Gaussian, and then I have a mixture component, the prior. And when you have two Gaussians, you only have one mixture component, because the other one is just 1 minus P. So you have 5. So that would be your P for two Gaussians in one dimension. And if you have a d-dimensional space, then the number of parameters is actually quadratic, because the covariance matrix is square in the number of dimensions. So that's how you determine P. And then L is the likelihood, right? So what you're doing is you're saying L is a measure of how well our model fits the data. And the more components you throw at it, the bigger L is going to be, because it's going to fit the data better and better and better. P is how complicated the model is, how many parameters you need to estimate for the model. So the more components you throw into the mixture, the more parameters you're going to have to estimate. So, and in both cases, whether it's Bayes information criterion or a Kaiki, AAC, or BIC, you're trying to maximize the quantity. So you're trying to make L big, right? So the minimum of minus L is you're making it big. You want to make the model fit the data, and you want to make P relatively small because you want the model to be as simple as possible. And this is a way to pick a trade-off, or one way to pick a trade-off between the complexity of the model, number of parameters, and how well it explains your data, the likelihood. So it's a really nice explanation. It's a feel-good kind of explanation. You read it and you say, this makes sense to me. Now I understand how to pick K. In practice, you use it. It's going to give you a number. You can use that number to pick K, and whether you're going to be happy with that K or not really varies, right? Because these, they have some theory behind them, but they're really rather arbitrary. So if you are not using a mixture model just for the purpose of using the mixture model, you are much better off doing the validation thing, right? So train it with different K, see what the error is on the validation set, or better yet, you're probably doing it to construct a new representation for your classifier. So take your classifier and see how well it works on the output of a mixture model over different values of K, and then pick the best K that way rather than using one of these, because these are not going to be optimal for that. Okay. All right, so let's summarize. We talked about mixture models, talked about the EM algorithm. We walked through 1D version, and we had an example for multiple dimensions. You can use it for real-valued data. If you do that, you use Gaussians. You can use it for discrete data, and there, instead of Gaussians, you would use multinomial distributions. And there are many examples of models like that. It's a probabilistic model, so it tries to fit the likelihood, which makes it nice. It is similar to k-means in many, many ways. So it is sensitive to starting points. So depending on where you start, you will end up in different configurations with different parameters for the Gaussians. So the objective is not convex. You're not always going to get to the same point. You will get to different points depending on where you start with. There is no natural stopping point. In k-means, you stop when the points don't change places. Here, there is no hard assignment of points to Gaussians, so what you have to do is you have to basically put a threshold, and once none of the probabilities change more than by a certain amount, then you decide to stop. Or if you have a big data set, you just run it for 5 iterations, or however much you have time for. And for K, you have a couple of ways of picking it, but it's not. I guess it's not much easier than with k-means. So how is it different from k-means? It is soft clustering, right? So you're not doing a hard assignment of one data point to one cluster. Each data point belongs to all the Gaussians to some degree. And the really big difference is you're estimating the covariance. And one way to think about what the estimate of variance does is as you are re-estimating the variance of each Gaussian, you're basically changing your definition of a distance between a centroid, which is the mean of the Gaussian, and each data instance. So you're changing your distance function as the algorithm progresses. So a good question to ask yourself, suppose you wanted, how can you cripple a mixture model to become exactly like k-means? Right. So what would you have to do to get the same output from a Gaussian mixture as you would from k-means? Any ideas?
The variance must be almost zero?
The variance must be almost zero. So that's interesting. Not sure that would do it by itself. But what would do it is if you just didn't recompute the variance. If you pegged the variance to 1 for everything, and you pegged the priors to be uniform, then the output of a Gaussian mixture model is going to be identical to the output of the k-means clustering algorithm.
Okay, guys, here we finished the mixture model and expectation maximization for another way of clustering using the Gaussian model. And now we will back to the dimensionality reduction. The handout of dimensionality reduction also available in OWL. So as based on our syllabus, we have to discuss the PCA, but it's good to know all of those. As I mentioned, the next topic would be anomaly detection, and we will explain my paper because I used the dimensionality reduction, I used the feature extraction concept, the feature selection topic in 2 algorithms, and then we use the learning curve, which is a new concept that would be the last topic in our course. So I hope that today we will be finalizing our course. If there is something that we need to have, maybe next week we'll have the first session. Okay, guys, I need to ask you today, would you like us to continue for today like in one session? I'll give you a break for like for 30 minutes by the end of the current session. Then we can immediately start the next session for 1.5 hours, which is enough. Or you would prefer to be from 2 to 3:30, for example, not 2 to 5. Or I would prefer to have a break, then we'll have 1.5 hours and you are free for today. What do you prefer? Answer me in chat, guys. Hello. Break, then 1.5 hour session. Okay, next 30 minutes break. Okay, more votes. Break. Okay, good. No, 1.5 hours is more than enough to finalize that topic. Is it clear, Hankon? Okay, so after we finish the dimensionality reduction, I'll give you a 30 minutes break, then we'll continue for 1.5 hours and we are done for today. So let's start with dimensionality reduction. Okay, Gurpreet, Yang, thank you guys. It seems that we are all on the same page. So let's continue with dimensionality reduction. Then we'll have a break, 30 minutes, then we'll continue. Let's continue.
Talking about a second type of unsupervised learning problem called dimensionality reduction. There are a couple different reasons why one might want to do dimensionality reduction. One is data compression, and as we'll see later, a few videos later, data compression not only allows us to compress the data and have it therefore use up less computer memory or disk space, but it will also allow us to speed up our learning algorithms. But first, let's start by talking about what is dimensionality reduction. As a motivating example, let's say that we've collected a dataset with many features, and I've plotted just 2 of them here. And let's say that unknown to us, 2 of the features were actually the length of something in centimeters, and a different feature, x2, is the length of the same thing in inches. So this gives us a highly redundant representation, and maybe instead of having 2 separate features, x1 and x2, both of which basically measure the length, maybe what we want to do is reduce the data to one-dimensional and just have one number measuring its length. In case this example seems a bit contrived, this centimeter and inches example is actually not that unrealistic and not that different from things that I see happening in industry. If you have hundreds or thousands of features, it's often just easy to lose track of exactly what features you have. And sometimes you may have a few different engineering teams. Maybe one engineering team gives you 200 features, a second engineering team gives you another 300 features, and the third engineering team gives you 500 features. So you have 1,000 features altogether, and it actually becomes hard to keep track of exactly which features you got from which team. And it's actually not that hard to have highly redundant features like these. And so if the length in centimeters was rounded off to the nearest centimeter and length in inches was rounded off to the nearest inch, then that's why these examples don't lie perfectly on a straight line, because of round off error to the nearest centimeter or the nearest inch. And if we can reduce the data to 1 dimensions instead of 2 dimensions, that reduces the redundancy. for a different example, again, maybe one that seems slightly less contrived, for many years I've been working with autonomous helicopter pilots, or I've been working with pilots that fly helicopters. And so if you were to do a survey or do a test of these different pilots, you might have one feature, X1, which is maybe the skill of these helicopter pilots, and maybe X2 could be the pilot enjoyment, that is, how much they enjoy flying, and maybe these two features will be highly correlated. And what you really care about might be this sort of this direction, a different feature that really measures, pilot aptitude. And I'm making up the name aptitude, of course, but again, if you have highly correlated features, maybe you really want to reduce the dimension. So let me say a little bit more about what it really means to reduce the dimension of the data from 2 dimensions, that is from 2D to 1-dimensional or to 1D. Let me color in these examples slightly different colors. And in this case, by reducing the dimension, what I mean is that I would like to find maybe this line, this direction on which most of the data seems to lie, and project all the data onto that line that I just drew. And by doing so, what I can do is just measure the position of each of the examples on that line, and what I can do is come up with a new feature, Z1, and to specify the position on the line, I need only one number. So Z1 is a new feature that specifies the location of each of those points on this green line. And what this means is that whereas previously, if I had an example X1, maybe this was my first example X1, so in order to represent X1, originally X1, I needed a 2-dimensional number, or a 2-dimensional feature vector. Instead, now I can represent Z1. I can use just Z1 to represent my first example, and that's going to be a row number. And similarly, X2, if X2 is my second example there, then previously, whereas this required 2 numbers to represent, if I instead compute the projection of that black cross onto the line, and now I need only one row number, which is Z2, to represent the location of this point Z2 on the line, and so on through my M examples. So just to summarize, if we allow ourselves to approximate the original dataset by projecting all of my original examples onto this green line over here, then I need only one number, I need only one row number to specify the position of a point on a line. And so what I can do is therefore use just one number to represent the location of each of my training examples after they've been projected onto that green line. So this is an approximation to the original training set because I have projected all of my training examples onto a line. But now I need to keep around only one number for each of my examples. And so this halves the memory requirement or the disk space requirement or what have you for how to store my data. And perhaps more interestingly, more importantly, what we'll see later in the later video as well is that this will allow us to make our learning algorithms run more quickly as well. And that is actually perhaps even the more interesting application of this data compression rather than reducing the memory or disk space requirement for storing the data. On the previous slide, we showed an example of reducing data from 2D to 1D. On this slide, I'm going to show another example of reducing data from 3-dimensional or 3D to 2-dimensional 2D. By the way, in a more typical example of dimensionality reduction, we might have 1,000-dimensional data or 1,000D data that we might want to reduce to, let's say, 100-dimensional, 100D. But because of the limitations of what I can plot on the slide, I'm going to use examples of 3D to 2D or 2D to 1D. So let's say I have a data set like that shown here, and so I would have a set of examples, xi, which are points in R3, so 3-dimensional examples. I know it might be a little bit hard to see this on the slide, but I'll show a 3D point cloud in a little bit. And it might be hard to see here, but maybe all of this data maybe lies roughly on the plane, like so. And so what we can do with dimensionality reduction is take all of this data and project the data down onto a two-dimensional plane. So here what I've done is I've taken all the data and I've projected all of the data so that it all lies on the plane. Now, finally, in order to specify the location of a point within a plane, we need two numbers, right? We need to maybe specify the location of a point along this axis and then also specify its location along that axis. So we need two numbers, maybe called Z1 and Z2, to specify the location of a point within a plane. And so what that means is that we can now represent each training example using two numbers that I've drawn here, Z1 and Z2. So our data can be represented using vectors Z, which are in R2. And these subscripts, Z subscript 1, Z subscript 2, what I just mean by that is that my vectors here, Z, are two-dimensional vectors, Z1, Z2. And so if I have some particular example, ZI, well, that's a two-dimensional vector, ZI1, ZI2. And on the previous slide, when I was reducing data to one-dimensional data, then I had only Z1, right? But and that's what the Z1 subscript on the previous slide was. But here I have two-dimensional data, so I have Z1 and Z2 as the two components of the data. Now, let me just make sure that these figures make sense. So let me just re-show these exact three figures again, but with 3D plots. So the process we went through was that shown in the left is the original dataset, in the middle the dataset projected onto 2D, and on the right the 2D dataset with Z1 and Z2 as the axes. Let's look at it a little bit further. Here's my original dataset, shown on the left, and so I had started off with a 3D point cloud like so. So where the axes are labeled X1, X2, X3. And so this is a 3D point cloud, but most of the data maybe roughly lies on, not too far from some 2D plane. So what we can do is take this data, and here's my middle figure. I'm going to project it onto 2D. So I've projected this data so that all of it now lies on this 2D surface. Okay, you can see all the data lies on a plane, because I projected everything onto a plane. And so what this means is that now I need only two numbers, Z1 and Z2, to represent the location of a point on the plane. And so that's the process that we can go through to reduce our data from three-dimensional to two-dimensional. So that's dimensionality reduction and how we can use it to compress our data. As we'll see later, this will allow us to make some of our learning algorithms run much later as well, but we'll get to that only in a later video. In the last video, we talked about dimensionality reduction for the purpose of compressing the data. In this video, I'd like to tell you about a second application of dimensionality reduction, and that is to visualize the data. For a lot of machine learning applications, it really helps us to develop effective learning algorithms if we can understand our data better, if we have some way of visualizing the data better. And so dimensionality reduction offers us often another useful tool to do so. Let's start with an example. Let's say we've collected a large data set of many statistics and facts about different countries around the world. So maybe the first feature, X1, is the country's GDP, or the gross domestic product. X2 is the per capita, meaning the per person GDP. X3, Human Development Index, life expectancy. X5, X6, and so on. And we may have a huge data set like this with, maybe 50 features for every country, and we may have a huge set of countries. So is there something that we can do to try to understand our data better? So I've given this huge table of numbers. How do you visualize this data? If you have 50 features, it's very difficult to plot 50-dimensional data. So what is a good way to examine this data? Using dimensionality reduction, what we can do is, instead of having each country represented by this feature vector, xi, which is 50-dimensional, so instead of, say, having a country like Canada, instead of having 50 numbers to represent the features of Canada, let's say we can come up with a different feature representation that is these z vectors that is in R2. If that's the case, if we can have just a pair of numbers, Z1 and Z2, that somehow summarizes my 50 numbers, maybe what we can do is then plot these countries in R2 and use that to try to understand the space and these sorts of features of different countries a little bit better. And so here, what you can do is reduce the data from 50 dimensions to 2D, so you can plot this as a two-dimensional plot. And when you do that, it turns out that if you look at the output of the dimensionality reduction algorithms, it usually doesn't ascribe a particular meaning to these new features Z1 and Z2. And it's often up to us to figure out, roughly what these features means. But if you plot what these features, here's what you might find. So here, every country is represented by a point Zi, which is in R2. And so each of those dots in this figure represents a country. And so here's Z1 and here's Z2. And highlight a couple of these. So we might find, for example, that the horizontal axis, the Z1 axis, corresponds roughly, to the overall country size or the overall economic activity of a country. So the overall GDP, overall economic size of a country. Whereas the vertical axis in our data might correspond to the per person GDP, or the per person well-being, or the per person economic activity. And you might find that given these 50 features, these are really the two main dimensions of variation. And so out here, you might have a country like the USA, which is a relatively large GDP, it's a very large GDP and a relatively high per person GDP as well. Whereas here, you might have a country like Singapore, which actually has a very high per person GDP as well, but because Singapore is a much smaller country, the overall economy size of Singapore is much smaller than the U.S. And over here, you would have countries where individuals are sort of unfortunately somewhat less well off, maybe shorter life expectancy, less healthcare, less economic activity, as well as smaller countries. Whereas a point like this would correspond to a country that has a substantial amount of economic activity, but where individuals tend to be somewhat less well off. But so you might find that the axes Z1 and Z2 can help you to more succinctly capture really what are the two main dimensions of variations amongst different countries, such as the overall economic activity of a country, reflected by the size of the country's overall economy, as well as the per person individual well-being measured by per person GDP, per person healthcare, and things like that. So that's how you can use dimensionality reduction in order to reduce data from 50 dimensions or whatever down to 2 dimensions or maybe down to 3 dimensions, so that you can plot it and understand your data better. In the next video, we'll start to develop a specific algorithm called PCA, or Principal Components Analysis. For the problem of dimensionality reduction, by far the most popular.
Now, guys, you see how what do we mean by dimensionality reduction, which means we minimize the number of features to the minimum number that we can visualize our data. Now we'll talk about principal component analysis. What the principal component analysis is? A feature extraction algorithm. What it will do, it will have new features that is extracted from the current features. So we'll have new features that is not part of the data set. However, the extracted feature will be built based on the algorithm. See how it will work.
By far the most commonly used algorithm is something called Principal Components Analysis, or PCA. In this video, I'd like to start talking about the problem formulation for PCA. In other words, let's try to formulate precisely exactly what we would like PCA to do. Let's say we have a data set like this. So this is a data set of examples X in R2, and let's say I want to reduce the dimension of the data from 2-dimensional to 1-dimensional. In other words, I would like to find a line onto which to project the data. So what seems like a good line onto which to project the data? It seems like a line like this might be a pretty good choice. And the reason we think this might be a good choice is that if you look at where the projected versions of the points go. So I'm going to take this point and project it down here and get that. This point gets projected here, to here, to here, to here. What we find is that the distance between each point and the projected version is pretty small. That is, these blue line segments are pretty short. So what PCA does formally is it tries to find a lower dimensional surface, really a line in this case, onto which to project the data so that the sum of squares of these little blue line segments is minimized. The length of those blue line segments, that's sometimes also called the projection error. And so what PCA does is it tries to find the surface onto which to project the data so as to minimize that. As an aside, before applying PCA, it's standard practice to first perform mean normalization and feature scaling so that the features x1 and x2 should have zero mean and should have comparable ranges of values. I've already done this for this example, but I'll come back to this later and talk more about feature scaling and mean normalization in the context of PCA later. But coming back to this example, in contrast to the red line that I just drew, here's a different line onto which I could project my data, which is this magenta line. And as you can see, this magenta line is a much worse direction onto which to project my data, right? So if I were to project my data onto the magenta line and get a set of points like that, and the projection errors, that is these blue line segments, would be huge. So these points have to move a huge distance in order to get onto the in order to get projected onto the magenta line. And so that's why PCA, principal components analysis, would choose something like the red line rather than like the magenta line down here. Let's write out the PCA problem a little more formally. The goal of PCA, if we want to reduce data from two-dimensional to one-dimensional, is we're going to try to find a vector that is a vector ui, which is going to be an Rn, so that would be an R2 in this case. I'm going to find the direction onto which to project the data so to minimize the projection error. So in this example, I'm hoping that PCA will find this vector, which I'm going to call U1, so that when I project the data onto the line that I define by extending out this vector, I end up with pretty small reconstruction errors, end up with sort of data that looks like this. And by the way, I should mention that whether PCA gives me U1 or negative U1 doesn't matter. So if it gives me a positive vector in this direction, that's fine. If it gives me sort of the opposite vector facing in the opposite direction, so that would be like minus U1. Let's draw that in blue instead. Right? Whether it gives me positive U1 or negative U1, it doesn't matter because each of these vectors defines the same red line onto which I'm projecting my data. So this is a case of reducing data from two-dimensional to one-dimensional. In the more general case, we have n-dimensional data and we want to reduce it to k dimensions. In that case, we want to find not just a single vector onto which to project the data, but we want to find k dimensions onto which to project the data so as to minimize this projection error. So here's the example. If I have a 3D point cloud like this, then maybe what I want to do is find vectors, so find a pair of vectors, and I'm going to call these vectors, let's draw these in red. I'm going to find a pair of vectors, so starting from the origin, here's U1, and here's my second vector, U2, and together these two vectors define a plane, or they define a 2D surface, right? Kind of like this sort of 2D surface onto which I'm going to project my data. For those of you that are familiar with linear algebra, for those of you that are really experts in linear algebra, the formal definition of this is that we're going to find a set of vectors, U1, U2, maybe up to UK, and what we're going to do is project the data onto the linear subspace spanned by this set of k vectors. But if you're not familiar with linear algebra, just think of it as finding k directions instead of just one direction onto which to project the data. So finding a k-dimensional surface, really finding a 2D plane in this case, shown in this figure, where we can define the position of a point in a plane using k directions, and that's why for PCA we want to find k vectors onto which to project the data. And so more formally, in PCA, what we want to do is find this way to project the data so as to minimize the sort of projection distance, which is the distance between the points and the projections. And so in this 3D example too, given a point, we would take the point and project it onto this 2D surface. We end up with that, and so the projection error would be, the distance between the point and where it gets projected down to my 2D surface. And so what PCA does is it'll try to find a line or a plane or whatever onto which to project the data to try to minimize that square projection, that 90-degree or that orthogonal projection error. Finally, one question I sometimes get asked is, how does PCA relate to linear regression? Because when explaining PCA, I sometimes end up drawing diagrams like these, and that looks a little bit like linear regression. It turns out PCA is not linear regression, and despite some cosmetic similarity, these are actually totally different algorithms. If we were doing linear regression, what we would do would be, on the left, we would be trying to predict the value of some variable y given some input features x. And so linear regression, what we're doing is we're fitting a straight line so as to minimize the squared error between a point and the straight line. And so what we'd be minimizing would be the squared magnitude of these blue lines. And notice I'm drawing these blue lines vertically, right? That these blue lines are the vertical distance between the point and the value predicted by the hypothesis. Whereas in contrast, in PCA, what it does is it tries to minimize the magnitude of these blue lines, which are, drawn at an angle. These are really the shortest orthogonal distances, the shortest distance between the point x and this red line. And this gives very different effects depending on the data set. And more generally, when you're doing linear regression, there is this distinguished variable y that we're trying to predict. That all that linear regression is about is taking all the values of x and trying to use that to predict y. Whereas in PCA, there is no distinguished, or there is no special variable y that we're trying to predict, and instead we have a list of features, x1, x2, and so on up to xn, and all of these features are treated equally. So no one of them is special. As one last example, if I have three-dimensional data and I want to reduce data from 3D to 2D, so maybe I want to find two directions, u1 and u2, onto which to project my data, then what I have is I have three features, x1, x2, x3, and all of these are treated alike. All of these are treated so symmetrically, and there's no special variable y that I'm trying to predict. And so PCA is not linear regression, and even though at some cosmetic level they might look related, these are actually very different algorithms. So hopefully you now understand what PCA is doing. It's trying to find a lower dimensional surface onto which to project the data so as to minimize this squared projection error, to minimize the squared distance between each point and the location of where it gets projected. In the next video, we'll start to talk about how to actually find this lower dimensional surface onto which to project the data. In this video, I'd like to tell you about the principal components analysis algorithm. And by the end of this video, you know how to implement PCA for yourself and use it to reduce the dimension of your data. Before applying PCA, there's a data pre-processing step which you should always take. Given a training set of m unlabeled examples, it's important to always perform mean normalization, and then depending on your data, maybe perform feature scaling as well. So this is very similar to the mean normalization and feature scaling process that we had for supervised learning. In fact, it's actually exactly the same procedure, except that we're doing it now to our unlabeled data x1 through xm. So for mean normalization, we first compute the mean of each feature, and then we replace each feature x with x minus its mean. And so this makes each feature now have exactly 0 mean. And then second, if the different features have very different scales. So for example, if x1 is the size of a house and x2 is the number of bedrooms, to use our earlier example, we then also scale each feature to have a comparable range of values. And so similar to what we had with supervised learning, we would take I subscript j, that's the j feature, and so we would subtract off the mean, that's what we have on top, and then divide by Sj. Here, Sj is some measure of the range of values of feature j. So it could be the max minus min value, or more commonly, it is the standard deviation of feature j. Having done this sort of data pre-processing, here's what the PCA algorithm does. We saw from the previous video that what PCA does is it tries to find a lower dimensional subspace onto which to project the data so as to minimize these squared projection errors. The sum of the square projection errors is the square of the length of those blue line segments. And so what we wanted to do specifically is find a vector u1 which specifies that direction, or in the 2D case we wanted to find two vectors u1 and u2 to define this surface onto which to project our data. So just as a quick reminder of what reducing the dimension of the data means, for this example on the left, we were given examples xi, which are in R2, and what we like to do is find a set of numbers zi in R with which to represent our data, right? So that's what reduction from 2D to 1D means. And so specifically, by projecting the data onto this red line there, we need only one number to specify the position of a point on the line. So I'm going to call that number z, or z1. Z here, this is a row number, so that's like a one-dimensional vector. So z1 just refers to the first component of this, one by one matrix, or this one-dimensional vector. And so we need only one number to specify the position of a point. So if this example here was my example x1, then maybe that gets mapped here, and if this example was x2, maybe that example gets mapped here, and so this point here would be z1, and this point here would be z2, and similarly, we would have those other points for these maybe x3, x4, x5 get mapped to z1, z2, z3. So what PCA has to do is we need to come up with a way to compute two things. One is to compute these vectors, u1, and in this case, u1 and u2. And the other is how do we compute these numbers z. So on the example on the left, we're reducing the data from 2D to 1D. In the example on the right, we would be reducing data from three-dimensional, so xi is in R3, to zi, which is now two-dimensional. So these z vectors would now be two-dimensional. So it would be z1, z2 like so. And so we need to give a way to compute these new representations, the z1 and z2 of the data as well. So how do we compute all of these quantities? It turns out that a mathematical derivation, or sort of a mathematical proof for what is the right value for u1, u2, z1, z2, and so on, that mathematical proof is very complicated and beyond the scope of the course. But once you've done all that math derivation, it turns out that the procedure to actually find the value of u1 that you want is not that hard, even though sort of the mathematical proof that this value is the correct value is somewhat more involved and more than I want to get into. But let me just describe the specific procedure that you have to implement in order to compute all of these things, the vectors u1, u2, and these vectors z. Here's the procedure. Let's say we want to reduce the data from n-dimensional to k-dimensional. What we're going to do is first compute something called the covariance matrix. And the covariance matrix is commonly denoted by this Greek alphabet, which is the capital Greek alphabet sigma. It's a bit unfortunate that the Greek alphabet sigma looks exactly like the summation symbol. So this is the Greek alphabet sigma. It's used to denote a matrix, and this here is a summation symbol. So hopefully in these slides there won't be ambiguity about which is sigma, the matrix, the covariance matrix, and which is a summation symbol. And hopefully it'll be clear from context, when I'm using each one. Having computed this matrix sigma, and let's say we were to store it in an octave variable called sigma, what we need to do is then compute something called the eigenvectors of the matrix sigma. And in octave, the way you do that is you use this command, usv equals svd of sigma. SVD, by the way, stands for singular value decomposition. This is much more advanced singular value decomposition this is much more advanced linear algebra than you actually need to know, but it turns out that when sigma is a covariance matrix, there are a few ways to compute these eigenvectors, and if you're an expert in linear algebra and if you've heard of eigenvectors before, you may know that there's another octave function called eig, which can also be used to compute the same thing. And it turns out that the SVD function and the I function will give you the same eigenvectors, only SVD is a little bit more numerically stable. So I tend to use SVD, although I have a few friends that use the I function to do this as well. But when you apply this to a covariance matrix sigma, they'll give you the same thing. That's because the covariance matrix always satisfies a mathematical property called symmetric positive semi-definite. You really don't need to know what that means, but the SVD and the I functions are different functions, but when they're applied to a covariance matrix, which can be proved to always satisfy this sort of a mathematical property, they'll always give you the same thing. Okay, that was probably much more linear algebra than you needed to know. In case none of that made sense, don't worry about it. All you need to know is that this is a command you should implement in Octave. And if you're implementing this in a different language than Octave or MATLAB, what you should do is find a numerical linear algebra library that can compute the SVD or singular value decomposition. And there are many such libraries, for probably all the major programming languages, and you should be able to use that to find a routine to compute the matrices U, S, and V given of the covariance matrix sigma. So just to fill in some more details, this covariance matrix sigma will be an n by n matrix. And one way to see that is if you look at the definition, this is an n by 1 vector, and this here, xi transpose, is 1 by n, and so the product of these two things is going to be an n by n matrix. Right, so it's 1 by n, is xi transpose 1 by 1 is 1 by n, so that's a n by n matrix, and when you add up a bunch of these, you still have an n by n matrix. And what the SVD outputs is 3 matrices, U, S, and V, and the thing we really need out of the SVD is the U matrix. So the U matrix will be also an n by n matrix, and if we look at the columns of the U matrix, it turns out that the columns of the U matrix will be exactly those vectors U1, U2, and so on that we want. So U will be an n by n matrix. And if we want to reduce the data from n dimensions down to k dimensions, then what we need to do is just take the first k vectors. And that will give us U1 up to UK, which are the k directions onto which we want to project the data. So to describe the rest of the procedure from this SVD numerical linear algebra routine, we get this matrix U, and I'm going to call its columns U1 through UN. So just to wrap up the description of the rest of the procedure, from the SVD numerical linear algebra routine, we get these matrices U, S, and V, and so here's the matrix U, and we're going to use the first k columns of this matrix to get U1 through UK. Now, the other thing we need to do is we need to come up with a way to take my original data set, X, which is in Rn, and find a lower dimensional representation, Z, which is in Rk for this data. So the way we're going to do that is I'm going to take the first k columns of the U matrix. So I'm going to construct this matrix. I'm going to stack up U1, U2, and so on up to UK in columns. It's really basically taking this part of the matrix, right? The first k columns of this matrix, and so this is going to be an n by k matrix. I'm going to give this matrix a name. I'm going to call this matrix U subscript reduce. It's sort of a reduced version of the U matrix, maybe. I'm going to use it to reduce the dimension of my data. And the way I'm going to compute Z is going to let Z be equal to this U reduced matrix transpose times X. Or alternatively, to write out what this transpose means, when I take the transpose of this U reduced matrix, what I'm going to end up with is these vectors now in rows. I have U1 transpose down to UK transpose, and then take that times X, and that's how I get my vector Z. just to make sure that these dimensions make sense, this matrix here is going to be k by n, and x here is going to be n by 1, and so their product here will be k by 1, and so z is k-dimensional, is a k-dimensional vector, which is exactly what we wanted. And of course, these x's here, right, can be examples in our training set, can be examples in our cross-validation set, can be examples in our test set. And for example, if I want to take training example I can write this as xi, and that's what will give me zi over there. So to summarize, here's the PCA algorithm on one slide. After mean normalization, it says ensure every feature is zero mean, and optionally feature scaling, which you really should do feature scaling if your features take on very different ranges of values. But so after this pre-processing, we compute the covariance matrix sigma, like so. And by the way, if your data is given as a matrix like this, if you have your data given in rows like this, if you have a matrix capital X, which is your entire training set written in rows, right, x1 transpose down to xm transpose, this covariance matrix sigma actually has a nice vectorized implementation, which that you can implement in octave. You can implement sigma equals 1 over m times x, which is this matrix up here, transpose times x, and this simple expression, that's a vectorized implementation for how to compute the matrix sigma. I'm not going to prove that this is a correct vectorization, but if you want, you can either numerically test this out yourself by trying out an octave and making sure that both this and this implementations give the same answers, or you can try to prove it yourself mathematically, either way. But this is a correct vectorized implementation for how to compute sigma. Next, we apply the SVD routine to get U, S, and V, and then we grab the first k columns of the U matrix to get U reduced. And finally, this defines how we go from a feature vector x to this reduced dimension representation z. And similar to k-means, if you're applying PCA, the way you'd apply this is with vectors x in Rn, right? So this is not done with the x0 equals 1 convention. So that was the PCA algorithm. One thing I didn't do was give a mathematical proof that this procedure actually gives the projection of the data onto the k-dimensional subspace, onto a k-dimensional surface that actually minimizes the square projection error. The mathematical proof of that is beyond the scope of this course, but fortunately the PCA algorithm can be implemented in not too many lines of octave code, and if you implement this in Octave or MATLAB, you actually get a very effective dimensionality reduction algorithm. So that was the PCA algorithm. One thing I didn't do was give a mathematical proof that the U1, U2, and so on, and the Z's and so on that you get out of this procedure is really the choices that will minimize the squared projection error, right? Remember we said what PCA tries to do is it tries to find a surface or a line onto which to project the data so as to minimize that squared projection error. So I didn't prove that this actually achieves that, and the mathematical proof of that is beyond the scope of this course. But fortunately, the PCA algorithm can be implemented in not too many lines of octave code. And
are you a software architect or solutions engineer? If not, this ad's not for you. If so,
in the PCA algorithm, we take n-dimensional features and reduce them to some k-dimensional feature representation. This number k is a parameter of the PCA algorithm. This number k is also called the number of principal components, or the number of principal components that we retain. And in this video, I'd like to give you some guidelines or sort of tell you about how people tend to think about how to choose this parameter k for PCA. In order to choose k, that is, to choose the number of principal components, here are a couple useful concepts. What PCA tries to do is it tries to minimize the average square projection error. So it tries to minimize this quantity, which I'm writing down, which is the difference between the original data x and the projected version x approx I, which was defined in the last video. So it tries to minimize the square distance between x and its projection onto that lower dimensional surface. So that's the average square projection error. Also, let me define the total variation in the data to be the average length squared of these examples xi. So the total variation in the data is, the average over my training set of the length of each of my training examples. And this sort of says, on average, how far are my training examples from the vector, from just being all zeros? So how far on average are my training examples from the origin? When we're trying to choose k, pretty common rule of thumb for choosing k is to choose the smallest value so that the ratio between these is less than 0.01. So in other words, pretty common way to think about how to choose k is we want the average square projection error, that is the average, the distance between x and its projections, divided by the total variation of the data, that is how much the data varies. We want this ratio to be less than, let's say, 0.01, or to be less than 1%, which is another way of thinking about it. And the way most people think about choosing k is, rather than choosing k directly, the way most people talk about it is as what this number is, whether this is 0.01 or some other number. And if this is 0.01, another way to say this, to use the language of PCA, is that 99% of the variance is retained. I don't really want to, don't worry about what this phrase really means technically, but this phrase 99% of the variance retained just means that this quantity on the left is less than 0.01. And so if you are using PCA, and if you want to tell someone, how many principal components you retained, it'd be more common to say, well, I chose K so that 99% of the variance was retained. And then that's kind of a useful thing to know. It means that, the average square projection error divided by the total variation, that was at most 1%. That's kind of an insightful thing to think about. Whereas if you tell someone that, well, I had 100 principal components, or K was equal to 100 in 1,000-dimensional data, it's sort of harder for people to interpret that. So this number 0.01 is what people often use. Other common values will be 0.05, and so this will be 5%. And if you do that, then you go and say, well, 95% of the variance was retained, and other numbers, maybe around 90% of the variance was retained, maybe as low as 85%. So that 90% would correspond to saying this to 0.10, and so kind of prevents 10%. And so range of values from 90, 95, 99, maybe as low as 85% of the variance retained would be a fairly typical range of values. And maybe a 95 to 99 is really the most common range of values that people use. And for many data sets, you'd be surprised, in order to retain 99% of the variance, you can often reduce the dimension of the data significantly still, and still retain most of the variance, because for most real-life data sets, many features are just highly correlated, and so it turns out to be possible to compress the data a lot and still retain 99% of the variance, or 95% of the variance. So how do you implement this? Well, here's one algorithm that you might use. We might start off, if you want to choose the value of k, we might start off with k equals 1, and then we run through PCA. So we compute ureduce, compute z1, z2 up to zm, compute all those x1 approx and so on up to xm approx, and then we check if 99% of the variance is retained. Then we're good, and we'll use k equals 1. But if it isn't, then what we'll do is we'll next try k equals 2. And then we'll again run through this entire procedure and check, is this expression satisfied? Is this less than 0.01? And if not, then we do this again. Let's try k equals 3, then try k equals 4, and so on until maybe we get up to k equals 17 and we find that 99% of the variance is retained, and then we use k equals 17, right? So that's one way to choose choose the smallest value of k so that 99% of the variance is retained. But as you can imagine, this procedure seems horribly inefficient. We're trying k equals 1, k equals 2, we're doing all these calculations. Fortunately, when you implement PCA, it actually, in a step, it actually gives us a quantity that makes it much easier to compute these things as well. Specifically, when you're calling SVD to get these matrices U, S, and V, when you're calling SVD on the covariance matrix sigma, it also gives us back this matrix S. And what S is going to be a square matrix, and n by n matrix, in fact, that is diagonal. So it's diagonal entries S11, S22, S33, down to SNN are going to be the only non-zero elements of this matrix, and everything off the diagonals is going to be 0. Okay, so those big O's that I'm drawing, by that what I mean is that, everything off the diagonal of this matrix, all of those entries there are going to be zeros. And so, what is possible to show, and I won't prove this here, but it turns out that for a given value of k, this quantity over here can be computed much more simply, and that quantity can be computed as 1 minus sum from I equals 1 through k of SII divided by sum from I equals 1 through n of SII. So just to say that in words, or just to take another view of how to explain that, if k equals 3, let's say, what we're going to do to compute the numerator is sum from I equals 1 through 3 of SII, so we just compute the sum of these first 3 elements, so that's the numerator. And then for the denominator, well, that's the sum of all of these diagonal entries. And 1 minus the ratio of that gives me this quantity over here that I've circled in blue. And so what we can do is just test if this is less than or equal to 0.01, or equivalently, we can test if sum from I equals 1 through k, SII divided by sum from I equals 1 through n, SII, if this is greater than or equal to 0.99, if you want to make sure that 99% of the variance is retained. And so what you can do is just slowly increase k, set k equals 1, set k equals 2, set k equals 3, and so on, and just test this quantity to see what is the smallest value of k that ensures that 99% of the variance is retained. And if you do this, then you need to call the SVD function only once, because that gives you the S matrix, and once you have the S matrix, you can then just keep on doing this calculation by increasing the value of k in the numerator, and so you don't need to keep on calling SVD over and over again to test out different values of k. So this procedure is much more efficient, and this can allow you to select the value of k without needing to run PCA from scratch over and over. You just run SVD once. This gives you all of these diagonal numbers, all of these numbers, S11, S22, down to SNN, and then you can just, vary k in this expression to find the smallest value of k so that 99% of the variance is retained. So to summarize, the way that I often choose k when I'm using PCA for compression is I would call SVD once on the covariance matrix, and then I would use this formula and pick the smallest value of k for which this expression is satisfied. And by the way, even if you were to pick some different value of k, even if you were to pick the value of k manually, maybe I have 1,000 dimensional data and I just want to choose k equals 100, then if you want to explain to others what you just did, a good way to explain the performance of your implementation of PCA to them is actually to take this quantity and compute what this is, and that will tell you what was the percentage of variance retained. And if you report that number, then people that are familiar with PCA, or people can use this to try to get a good understanding of how well your 100-dimensional representation is approximating your original data set, because it's 99% of variance retained. That's really a measure of your square reconstruction error, that ratio being at most 0.01, and this gives people a good intuitive sense of whether your implementation of PCA is finding a good approximation of your original data set. So hopefully that gives you an efficient procedure for choosing the number k, for choosing what dimension to reduce your data to. And if you apply PCA to very high dimensional data sets, to like 1,000 dimensional data, very often, just because data sets tend to have highly correlated features, this is just a property of most of the data sets you see, you often find that PCA will be able to retain 99% of the variance, or retain 95, 99, some high fraction of the variance, even while compressing the data by a very large factor. In some of the earlier videos, I was talking about PCA as a compression algorithm, where you may have, say, 1,000-dimensional data and compress it to 100-dimensional feature vector, or have 3-dimensional data and compress it to a 2-dimensional representation. So if this is a compression algorithm, there should be a way to go back from this compressed representation back to an approximation of your original high dimensional data. So given Zi, which may be 100 dimensional, how do you go back to your original representation Xi, which was maybe 1,000 dimensional? In this video, I'd like to describe how to do that. In the PCA algorithm, we may have an example like this. So maybe that's my example X1, and maybe that's my example X2. And what we do is we take these examples and we project them onto this one-dimensional surface, and then now we need to use only a row number, say Z1, to specify the location of these points after they've been projected onto this one-dimensional surface. So given a point like this, given a point Z1, how can we go back to this original two-dimensional space? And in particular, given a point Z, which is in R, can we map this back to some approximate representation X in R2 of whatever the original value of the data was? So whereas Z equals U reduced transpose X, if you want to go in the opposite direction, the equation for that is we're going to write X approx equals U reduce times Z. And again, just to check the dimensions, here U reduce is going to be an n by k dimensional vector. Z is going to be a k by 1 dimensional vector. So when you multiply these out, that's going to be n by 1. And so X approx is going to be an n dimensional vector. And so the intent of PCA, that is if the square projection error is not too big, is that this X approx will be close to whatever was the original value of X that you had used to derive Z in the first place. To show a picture of what this looks like, this is what it looks like. What you get back of this procedure are points that lie on the projection of that, onto the green line. So to take our early example, if we started off with this value of x1, and we got this value of z1, if you plug z1 through this formula to get x1 approx, then this point here, that would be x1 approx, which is going to be in R2, and so, and similarly, if you do the same procedure, this would be X2 approx, and you know, that's a pretty decent approximation to the original data. So that's how you go back from your low dimensional representation Z back to an uncompressed representation of the data. You get back an approximation to your original data X. And we also call this process reconstruction of the original data, where we think of trying to reconstruct the original value of X from the compressed representation. So, given an unlabeled dataset, you now know how to apply PCA and take your high dimensional features X and map it to this lower dimensional representation Z. And from this video, hopefully you now also know how to take these lower representations Z and map it back up to an approximation of your original high dimensional data. Now that you know how to implement and apply PCA, what I'd like to do. In an earlier video, I had said that PCA can be sometimes used to speed up the running time of a learning algorithm. In this video, I'd like to explain how to actually do that, and also say some, try to give some advice about how to apply PCA. Here's how you can use PCA to speed up a learning algorithm, and this supervised learning algorithm speed up is actually the most common use of that I personally make of PCA. Let's say you have a supervised learning problem. Notice this is a supervised learning problem with inputs X and labels Y. And let's say that your examples Xi are very high dimensional. So let's say Xi are 10,000 dimensional feature vectors. One example of that would be if you were doing some computer vision problem where you have 100 by 100 images, and so if you have 100 by 100, that's 10,000 pixels, and so if Xi are feature vectors that contain your 10,000 pixel intensity values, then you have 10,000 dimensional feature vectors. So with very high dimensional feature vectors like this, a learning algorithm can be slow, right? Just if you feed 10,000 dimensional feature vectors into logistic regression or a neural network or support vector machine or what have you, just because that's a lot of data, that's 10,000 numbers, it can make your learning algorithm run more slowly. Fortunately, with PCA, we'll be able to reduce the dimension of this data and so make our algorithms run more efficiently. Here's how you do that. We're going to first take our labeled training set and extract just the input. So we're just going to extract the x's and temporarily put aside the y's. So this will now give us an unlabeled training set. So that's x1 through xm, which are maybe there's a 10,000 dimensional data, 10,000 dimensional examples that we have. So just extract the input vectors x1 through xm. Then we're going to apply PCA, and this will give me a reduced dimension representation of the data. So instead of 10,000 dimensional feature vectors, I now have maybe 1,000 dimensional feature vectors. So that's like a 10x savings. So this gives me, if you will, a new training set. So whereas previously I might have had an example x1, y1, my first training input is now represented by z1, and so I'm going to have a new sort of training example, which is z1 paired with y1, and similarly z2, y2, and so on up to zm, ym, because my training examples are now represented with this much lower dimensional representation, z1, z2, up to zm. Finally, I can take this reduced dimension training set and feed it to a learning algorithm, maybe a neural network, maybe logistic regression, and I can learn a hypothesis H that takes as input these lower dimensional representations Z and tries to make predictions. And so if I were using logistic regression, for example, I would train a hypothesis that outputs 1 over 1 plus e to the negative theta transpose Z, or theta transpose Z, that takes as input to one of these z vectors and tries to make a prediction. And finally, if you have a new example, maybe a new test example x, what you do is you would take your new test example x, map it through the same mapping that was found by PCA to get you your corresponding z, and that z then gets fed to this hypothesis, and this hypothesis then makes a prediction on your input x. One final note. What PCA does is it defines a mapping from x to z. And this mapping from x to z should be defined by running PCA only on the training set. And in particular, this mapping that PCA is learning, right, this mapping, what that does is it computes a set of parameters, right? There's the feature scaling and mean normalization, and there's also computing this matrix U reduce. But all of these things, like U reduce, that's like a parameter that is learned by PCA, and we should be fitting our parameters only to our training set and not to our cross-validation or test sets. And so these things, the U reduce and so on, that should be obtained by running PCA only on your training set, and then having found U reduce, or having found the parameters for feature scaling, right, the mean normalization and scaling, the scale that you divide the features by to get them onto comparable scales. But having found all those parameters on the training set, you can then apply the same mapping to other examples that may be in your cross-validation set or in your test set. Okay, but so just to summarize, when you're running PCA, run your PCA only on the training set portion of your data, not the cross-validation set or the test set portion of your data, and that defines the mapping from X to Z, and you can then apply that mapping to your cross-validation set and your test set. And by the way, in this example, I talked about reducing the data from 10,000 dimensional to 1,000 dimensional. This is actually not that unrealistic. For many problems, we can actually reduce the dimension of data, by 5x, maybe by 10x, and still retain most of the variance. And we can do this with barely affecting the performance in terms of classification accuracy, let's say, barely affecting the classification accuracy of the learning algorithm. And by working with low dimensional data, our learning algorithm can often run much, much faster. To summarize, we've so far talked about the following applications of PCA. First is the compression application, where we might do so to reduce the memory or the disk space needed to store data. And we just talked about how to use this to speed up a learning algorithm. In these applications, in order to choose K, often we'll do so according to figuring out what is the percentage of variance retained.
On Adapted Mind Reading, stories are designed to build vocabulary and comprehension. And
so is for this learning algorithm speed up application, often will retain 99% of the variance. That would be a very typical choice for how to choose K. So that's how you choose K for these compression applications. Whereas for visualization applications, well, usually we know how to plot only two-dimensional data or three-dimensional data. And so for visualization applications, we would usually choose K equals 2 or K equals 3 because, we can plot only 2D and 3D data sets. So that summarizes the main applications of PCA as well as how to choose the value of K for these different applications. I should mention that there's one frequent misuse of PCA. And you sometimes hear about others doing this, hopefully not too often, but just want to mention this so that you know not to do it. And there's one bad use of PCA, which is to try to use it to prevent overfitting. Here's the reasoning. This is not a great way to use PCA, but here's the reasoning behind this method, which is, if we have xi, then maybe we'll have n features, but if we compress the data and use zi instead, then that reduces the number of features to k, which could be much lower dimensional. And so if we have a much smaller number of features, if k is 1,000 and n is 10,000, then if we have only 1,000 dimensional data, maybe we're less likely to overfit than if we were using 10,000 dimensional data with like 1,000 features. And so some people think of PCA as a way to prevent overfitting, but just to emphasize, this is a bad application of PCA, and I do not recommend doing this. And it's not that this method works badly. If you were to use this method to reduce the dimension of data to try to prevent overfitting, it might actually work okay. But this just is not a good way to address overfitting. And instead, if you're worried about overfitting, there's a much better way to address it, to use regularization instead of using PCA to reduce the dimension of your data. And the reason is, if you think about how PCA works, it does not use the labels Y, right? You're just looking at your inputs XI and you're using that to find a lower dimensional approximation to your data. So what PCA does is it throws away some information. It throws away or reduces the dimension of your data without knowing what the values of Y is. So this is probably okay. Using PCA this way is probably okay if, say, 99% of the variance retained, if you're keeping most of the variance, but it might also throw away some valuable information. And it turns out that if you're retaining 99% of the variance or 95% of the variance or whatever, it turns out that just using regularization will often give you at least as good a method for preventing overfitting, and regularization will often work better, because when you're applying linear regression or logistic regression or some other method with regularization, this minimization problem actually knows what the values of Y are, and so is less likely to throw away some valuable information, whereas PCA doesn't make use of the labels and is more likely to throw away valuable information. So just summarize, it is a good use of PCA if your main motivation is to speed up your learning algorithm, but using PCA to prevent overfitting, that's not a good use of PCA, and using regularization instead is really what many people will recommend doing instead. Finally, one last misuse of PCA. So I should say PCA is a very useful algorithm. I often use it, for the compression or the visualization purposes, but what I sometimes see is also people sometimes use PCA where it shouldn't be. So here's a pretty common thing that I see, right? Which is if someone's designing a machine learning system, they may write down a plan like this. Let's design a learning system. Get a training set, and then what I'm going to do is run PCA, then train logistic regression, and then test on my test data. So often at the very start of a project, someone will just write out a project plan that says, let's do these 4 steps with PCA inside. Before writing out a project plan that incorporates PCA like this, one very good question to ask is, what if we were to just do the whole thing without using PCA? And often people do not consider this step before coming up with a complicated project plan and implementing PCA and so on. And so specifically, what I often advise people is, before you implement PCA, I would first suggest that do whatever it is, take whatever it is you want to do, and first consider doing it with your original raw data XI. And only if that doesn't do what you want, then implement PCA and consider using ZI. So before using PCA, instead of reducing the dimension of the data, I would consider, let's ditch this PCA step, and I would consider, let's just train my learning algorithm on my original data. Let's just use my original raw input xi. And I would recommend, instead of putting PCA into the algorithm, just try doing whatever it is you're doing with the xi first. And only if you have a reason to believe that doesn't work. So only if your learning algorithm ends up running too slowly, or only if the memory requirement or the disk space requirement is too large, so you want to compress your representation. But only if using the xi doesn't work, only if you have evidence or a strong reason to believe that using the xi won't work, then implement PCA and consider using the compressed representation. Because what I do see is sometimes people start off with a project plan that incorporates PCA inside, and sometimes whatever they're doing would have worked just fine even without using PCA instead. So just consider that as an alternative as well before you go and spend a lot of time to implement PCA and figure out what K is and so on. So that's it for PCA. Despite these last sets of comments, PCA is an incredibly useful algorithm when you use it for the appropriate applications, and I actually use PCA pretty often, and for me, I use it mostly to speed up the running time of my learning algorithms, but I think almost just as common an application of PCA is to use it to compress data, to reduce the memory or disk space requirements, or to use it to visualize data. And PCA is one of the most commonly used and one of the most powerful unsupervised learning algorithms. And with what you've learned in these videos, I think hopefully you'll be able to implement PCA and use them to all of these purposes as well. In an earlier video, I had said that PCA can be sometimes used to speed.
Hello, guys. So we reached to the end of PCA, and we see that PCA is extracting a new features from the current set of features based on the variance. And we see how the procedure is working. There are another way that we call it feature selection. I'll touch base on it in the next session with the anomaly detection thing. So it's now 11:24. We will meet back at 12 to discuss the anomaly detection with feature selection and the learning curve using my one of anomaly detection published research paper. So we'll discuss those things through the part. If you have any question, please don't hesitate to ask. If you don't, see you at 12. By the way, guys, join the extra class link. I'll just send an announcement a few minutes later. You are free to leave if you don't have any question. I'll stop recording here.